Morning, everyone. Welcome. Welcome to on this glorious day. Blue sky outside for those of you online that aren't in Sydney. My name is Martin Ugander. I'm the convener of the Sydney Clinical Imaging Network. And today we have our Sydney Clinical Imaging Summit 2024. Last time we met in this forum was a year and a half ago, and there's been a lot of exciting developments, both within the network and the research output that's an activity that's going on within the network. But I'd like to start with acknowledging the traditional custodians of the lands on which we meet, the Gadigal people of the Eora Nation, or of the many lands on which we meet, where you're coming from today via Zoom for this hybrid meeting. I also like to acknowledge any Indigenous or Aboriginal individuals with us here today, and leaders past, present, and emerging. So moving on to the network and what's been going on. This is a brief update on where we stand and things that have developed since last, before we get into the meat of the program today. So just a little bit of a reminder in our imaging matrix, our 3D matrix. For those of you that haven't seen this before, who are new to the network, we have on one axis technical development, preclinical imaging, and clinical imaging. On the other axis, different imaging modalities, here represented by MRI, CT, nuclear, and ultrasound. And then we have another axis of different organs, the heart, the brain, etc. And this 3D box or 3D matrix represents sort of all of the imaging that we do. Here in skin, we focus on this front face here. Of course, we dabble into the preclinical and technical development for doing our human imaging, but the focus of our network is clinical imaging, and it's imaging with the body imaging modalities of the radiological space, if we want to call it that. Our vision, as a repetition, is to make the University of Sydney a national and international leader in clinical imaging research and education. So we know from the Australians' ranking, for whatever for whatever that's worth, they did a ranking of imaging across universities in Australia, and there we rank the best, which is a great feeling and something we should be proud of. However, we shouldn't rest on our laurels just because of that. There's plenty of opportunity for growth upwards, and I don't think we should measure ourselves based on the relative merits within Australia. We should have ambitions and a compass direction of our own. The purpose that we have identified in the network is, I'll read it out just because it's a little bit of a mouthful, but just to remind us all. The purpose of the network is to curate a critical mass of diverse clinical imaging clinicians, researchers, and educators. And through digital and physical meetings, interfaces, forums, courses, resources, communication, it's like the summit today, and many other types of activities, promote a culture of excellence in clinical imaging research and education in order to improve health and healthcare provision. It's a lofty purpose, but one that I certainly sign on under, and I hope you do too. So there's been some changes in the leadership group. We did a major revamp and brought in a cadre of EMCRs and in some cases some seniors. If you would, if you're here today in the audience, I'd like for you to just stand up and give a wave. Mariano Cabezas, Mark Dennis, I know can't make it. Nicola Gianotti. Lingwei Elvi, Junman Kim, Eli Matar, I know is overseas, Payman Obeidi, Ramon Landin Romero, David Waddington, Sirisha Tarimala, Sikong Tu, Luping Shu, Tess Reynolds, and myself, Veronica Wong. Veronica Wong, are you here? She might be online. Yeah. So there's been a revamp of our leadership group. I'd like you to the reason I put the faces up here, take the opportunity and grab onto one of these many talented individuals in the breaks for the informal discussions, and think about what you want to bring to Skin, not only what Skin can bring to you. We'll get to that, but I want to encourage you to have that conversation. Also, we've created a number of roles over the past year, and we're launching here today to sort of tell about them, different interest groups. On the one hand, we have David Waddington and Sirisha Tarimala steering up the MRI technology special interest group, which is, as it sounds, for MRI imaging, image acquisition, reconstruction, and image analysis. We have a brain imaging interest group with the fantastic acronym BIG under the leadership of Ramon Landin Romero. We have commercializations and partnerships under the guidance of Payman Obeidi. We have our Faculty of Medicine and Health EMCR showcase representative in Nicola Giannotti. And so, as you may recall, last year, towards the end of the year, I believe it was in November, December, the Faculty of Medicine and Health had an EMCR showcase of research, not too dissimilar from what we are doing here today, but focusing on broadly across the entire faculty. And so we had a clinical imaging representation there in presentations. And if you already now know of yourself or someone else that might be in the EMCR position that wants to get involved and showcase their research at the EMCR showcase, please do reach out to Nicola, because this is absolutely an opportunity for self-nomination to get representatives from Skin for that event. Also, we have the Cardiovascular Magnetic Resonance Special Interest Group under the leadership of Mark Dennis. He's not here, but he looks like that on the picture. Also, a little bit of an announcement for those of you attending the International Society of Magnetic Resonance in Medicine, the ISMRM, coming up in Singapore in May. The MRI Technologies Group has organized a Skin meetup on the Monday of the meeting at 7 p.m. at the District 10 Bar and Grill next to the Convention Center for those who are interested. If you don't recall this in particular, reach out to David Waddington or Sirisha Tarimala. They'll certainly remind us of that. Finally, I'd like to close with this picture and the quote below it. And remember, ask not what your anthill can do for you, but what you can do for your anthill. So Skin is our anthill, and we can ask of it to help us out with the things we want to do, but we might have an ambition of what we want to do with it. I'd like, because Skin is nothing more than us who are involved in it. And if you're sitting there thinking, you know, I'd like to start a special interest group for blank imaging of blank organ or blank interest, whatever it may be, there is an opportunity to do that. We don't have many reins limiting us on what we want to do. So please feel that opportunity is there. Reach out to myself or any of the members of the leadership group, because that I encourage you to do that, because we can make of it what we want. And again, down there on the bottom, nominations for the EMCR speakers for coming up towards the end of the year can be sent into our role email address, or reached out to Nicola Giannotti should you want to do that. And with that, I'd like to close the welcome, if you will, and invite the first speaker, Fernando Calamante, who will be speaking on an update from the Sydney imaging infrastructure that we have.
Good morning, everyone, and good morning those who's online. I was asked to give an update of Sydney imaging, but I'm also including what Sydney imaging is, because I don't know if all of you are familiar with Sydney imaging. So Sydney imaging is one of the 8 core research facilities that the university has. We support biomedical imaging research, and we're organized in 3 sectors, if you want: preclinical imaging, hybrid theater, and the clinical imaging. Should I try now? Yeah, so preclinical imaging, hybrid theater, and clinical imaging. So very briefly, because it would take a bit of time, but you can find all this information also on the website. Preclinical imaging is, as the name you can imagine, is to support research on animal models, both ex vivo and in vivo. On the left, you have a list of the equipment that we have and some of the things that we are developing now. And on the right, just a few example pictures of what we can, the type of machines we can support, obviously just a subset of the things that we can support. On the hybrid theater side, is a fully equipped hybrid theater. You see there on the top right, is to support primarily large animal research, translational research, but it also do a lot of other work too. And again, you see in the left, and you can find it in the website, a big range of equipment. We have image-guided surgery equipment, we have robotic surgery equipment, and a lot of other equipment there you can see. On the clinical imaging side, the big thing that we recently got is the whole body PET. And I won't be talking a lot because Steve is talking in the next session, a whole talk about that. But yeah, many of you may have heard we had a series of webinars and a launch symposium. So if you go to that QR code or our website again, you can have all the recordings and get information of what we can do. Importantly, this total body PET was a partnership between the National Imaging Facility, the University of Sydney, and the Northern Sydney Local Health District. And I'll talk in a moment also about the radiochemistry side. So for those of you who are not familiar with the National Imaging Facility, is one of the EMCRs facilities that the federal government supports. There are 14 nodes of this NIF network. We are one of them that is spread throughout Australia. So through them, you can access the equipment that we have at Sydney Imaging, but also the equipment that any of these other facilities have throughout Australia, and they support also multi-site studies. From a practical point of view, NIF contributes two things also. Contributes funding, which is very important for us, so co-investing in particular for total body PET and radiochemistry, that I'll mention in a moment. And also co-funds 4 of our fellows that support the research, and they are, I think they're all here today. Oh, yes. So you'll see them, or you can go and talk to them through other things. So they support different aspects of our facility. And the last 2 also are heavily involved with the Australian Machine Service that Ryan will be talking a lot more about the Australian Machine Service in the next presentation. From where we're going, and some of you may have seen this slide because this has been long coming, hopefully now we are getting to the point where it will happen, is the next big priority for Sydney Imaging has been, and it's been for many years, a 3 Tesla MRI scanner next to the hybrid theater. So for those of you who are familiar with the hybrid theater, that's Charles Perkins Centre, if that's a theater, there is a cold shell space next to the hybrid theater. And that's where the 3 Tesla would go. And that is that you can use it as either an interventional facility or close that wall and use it as 2 simultaneous facilities. Animals coming from the right, humans using the scanner on the rest and the left. And all has been designed to be simultaneously used. So that hopefully it is finally going to happen. The other one that is happening literally while we speak is we are revamping opening up the radiochemistry facility. There are 2 of these facilities. One that is the one that is happening now is at the Bremerman Center. So if you're familiar with the Bremerman Center, this is building H. There are a bunch of things, in particular hot cells and other things. But for you to have an idea, if you're familiar with the facility, that room is where we have the PET-MR, and that there at the top is where the animals can be held. So as you can see, the radiochemistry facility will be literally adjacent to the other 2 facilities. And then the other one that we're in discussion and setting up probably later in the year is at the Royal North facility to support work at the total body PET. And again, it would be very close proximity to the total body PET. And National Imaging Facility is heavily involved also in this part of the facility. So what I wanted to give you, end up here with, hopefully what you get the picture is that Sydney Imaging can support a kind of a translational thing. You can go from preclinical to hybrid theater to clinical, preclinical to clinical, and so on. Or obviously you don't need to do the translation. And just to give you a flavor, for example, one of the type of things that we're going to be able to support this year is development of radio tracers. So for example, you're going to be able to do radio labeling in our radiochemistry facility, then use our PET-MR or whole body preclinical PET-CT to do whole body biodistribution, and then also translate to first human studies at the total body PET that Steve will be talking later this morning. So with that, I'll finish. That's the QR code, or obviously put in Google Sydney Imaging, and these are the people that you can, if you need to talk to us for various things, you can get in touch with us. Thanks for your attention.
Before you leave, Fernando, I'm going to be a little bit cheeky. So the number one question I get from researchers across the university is, when's the 3T coming? Could you give us any kind of hint, or what are your thoughts?
Yeah, I mean, the reality is it's not going to happen before the end of the year. And the reason is the work. So many of you, if any of you are doing any refurbishing of your house, any change, now the prices have rocketed. So we are now in a crazy situation where doing the room is more expensive than buying equipment, and that's happening to any of the research facilities. So, it used to be that the main concern was buying the scanner. Now the main concern is building the place. So that's what things are now much slower, not for us, but for all the research facilities in all the universities. Everything takes longer now. But yeah, hopefully end of the year.
We're very thankful for the efforts you put into making that happen. So thanks, Fernando. The next speaker we have today is Ryan Sullivan. Welcome, Ryan. He will introduce himself, but he will be speaking on the imaging services infrastructure that we have. Welcome, Ryan.
So a bit of background, the Australian Imaging Service started as a small project just to set up XNAT for a couple of researchers in the Brain and Mind Centre at the University of Sydney. From there, we had substantial increased investments and soft launch last year. And now we're moving to the next phase. We're funded by the MRFF Critical Research Infrastructure and the European Horizon Infrastructure. So AIS. The goal of AIS is to build and implement a national federation so that when you're doing multi-site studies, both in Australia and internationally, you have a common data framework, a common set of tools and pipelines so that when you're running quality control analysis across thousands of patients, it is the exact identical set of software running across all those sites. So our main focus is increasing the adoption of innovative but trusted techniques. Often you'll see a paper in Nature, Science, pick your favorite journal, the reference on all this cool stuff they did, and then you have to try to find the code, get it working, usually doesn't work. That's a real pain point. So what we're trying to do is build up libraries of tools, pipelines, applications, and making them accessible and reusable across multiple universities nationwide, and making everything accessible directly in the browser so that all the backend, setting up of GPUs, computational resources, data movement is handled for you to drive the accessibility of these tools, because not everyone has a pocket postdoc to do all this for them. So AIS works as a federation. So we build a single national open source product, which multiple universities can deploy. So currently we have 13 production environments across 12 different universities, currently deployed in Australia, the US, and the EU. And we support about 460 users right now across about 660 research projects. And so how it functions is we have central university nodes that store the data long-term, provide user access, provide the tools, which I'll talk about, along with edge devices where we can put in an application, say in IMED Radiology in New South Wales Health, and that acts as a gateway to push DICOM data, case-based data, list mode from the clinical instruments to the university in a secure way that's approved by the state health bodies. Just an overview of the number of universities that are currently involved in this. So AIS has 4 capability areas. Many of you may be familiar with XNAT, which is just the data management aspect. But importantly, we've built a data-centric computing framework where instead of having the data in one location, and it's on the user to bring that data to an HPC environment and do everything separately, we bring the computes to the data. So the first service is data management with XNAT. The second service is traditional kind of batch-based processing with pipelines using our Kana and Pydra framework led by Thomas Close and Sydney Imaging. This is your automated QC file conversion, bulk processing that you want to do, consistently across 1,000 patients. The third area, which is currently in testing, is being able to launch full secure virtual desktops so we can analyze identifiable health data directly on the data. So you don't need to download it to your workstation or to VRD or to Artemis. You can just spin up multiple flavors of virtual desktop directly on the data and analyze it in the browser. And that will come preloaded with a set of tools from Neurodesk. And lastly, we are integrating Monai Label for AI-assisted annotation and segmentation, along with NVIDIA Flare for federated learning. So overview of pipeline, being able to package any arbitrary number of steps into a set of containers and running those consistently and being able to schedule them so that when a 3T MRI comes off from, say, iMed Radiology, it's de-identified, you run your QC, you run any pre-processing, and it's ready to go in the virtual desktop. The interactive analysis, we have two options. One is Jupyter environments, again, running on your data directly in XNet. And the newer one is Neurodesk. So we just published this in Nature Methods in January this year. So what it does is it gives you full reproducibility on the entire software stack and versioning for all the applications, because version drift has been shown to be a source of error in computation. So if you have a project you're working on for 1 or 2 years, while you might be pulling the latest Python packages in the background, there'll be discrepancies in how the mathematics is calculated behind the scenes. So this allows you to really lock down those versions. And whether you're running on also an imaging service, Nectar Cloud, commercial cloud, the software will be bitwise identical. We're expanding the viewers on AIS. So the XNet has the built-in OHIP viewer, but we're adding a 3D Slicer, QPath, CVAT, and welcome any recommendations for other viewers. And importantly, being able to integrate these viewers directly with the Monai Label suite. So you can run pre-trained PyTorch models within these viewers, spinning up GPU clusters in the background, and indeed train your own models to add to the available zoo. The main focus of our MRFF, so we've privacy is a large issue, particularly in clinical studies. One of the main ones we're looking at now has 400 patients a week who are naked. They don't want to share that data with 15 postdocs to develop AI for obvious reasons. So what we are doing is implementing kind of 4 streams of work. The first is around a global participant ID. So instead of manually having an Excel sheet or REDCap where you have your patient name and your patient ID, being able to automatically mint those and bifurcate them as they leave the clinical site and integrate REDCap projects directly with XNet projects so you can have bi-directional flow of information for coordination of trials. Second is implementing a suite of NLP tools for de-identification and de-risking, building up a risk profile for your patient over an entire cohort before you want to share it. So looking at what's the text data in the DICOM headers, in the patient reports, to give you some idea of, is there data and privacy leakage in your data set? Having seen lots of people's data, there usually is, unfortunately. And lastly, federated learning, so we can do distributed machine learning across clinical sites, across universities, or even within the university without sharing the data sets. And then linking all these together with genomics and pathology data. So last slide, particularly for federated learning, we're working with Flera, which is a group that has developed out of a previous MRFF infrastructure program. And in this case, we'll be deploying NV-Flare to do federated learning across 15 sites, so 5 in Queensland Health, 5 in New South Wales, 3 of which are New South Wales Health, and 5 in Victoria to be able to support the ACRF ACEMED. Lastly, for contact, AISadmin is the main email. And then from there, we kind of break it down to myself and the new operations manager for any partnerships, projects, how to work with us. Dr. Tom Close for analysis informatics, building pipelines, adding new tools, and tapping into the larger national imaging facility network. And then Feng Zhu for any technical support, troubleshooting, and performance. Thank you.
Thanks so much, Ryan, for that. You know, what I really like about the offerings that you have is that you span the spectrum of the high end, really bleeding edge stuff, but then also to the more absolute, just bare bones basic. And for those of us who are new in the audience online or here, just to be able to have a research PACS that you can connect your scanner to is amazing. All this stuff, who's paying for it? Do we have to pay as researchers to use it?
Depends on the scale. So data storage, like with RDS, is covered essentially by the DVCR. When you get to, you know, where your data set's measured in petabytes, we do ask for some cost recovery. So for the ACRF AceMed, you know, they're producing 1/4 of a petabyte a year. The total body PET produces 3/4 of a petabyte if we kept all the list modes. So at that point, yeah, when it's measured in petabytes, we start to look at cost recovery, but otherwise data is included like RDS, and similar for computation. For kind of base pipelines, base virtual desktops, it's included. If you want a couple A100s, there's going to be some cost recovery. So it's just a conversation.
So basically, if you're a beginner EMCR and want to start your own research group, but you just need a research PACS for a couple hundred studies for the first day,
cost.
No cost. That's free. Free as in beer free. So yeah, thank you, Ryan. Of course, it's not Ryan himself paying it out of his own pocket. We thank the university and the funders who have been giving funding to Ryan to develop these tools for us, which are so helpful. Thank you, Ryan. And our next speaker, I'd like to invite up Cheryl Foster. Cheryl's from the Westmead Institute, and please tell us about what's going on in Westmead, because there's stuff beyond Camperdown, I hear.
Easy. Thank you. Hi, everyone. Nice to be here. Yes, there are things happening outside Camperdown. So I work at Westmead Hospital as well as working here at the discipline of medical imaging at the university. We have a 3T scanner out at Westmead Hospital, which we do primarily research within the clinical department. So we have a number of scanners out at Westmead Radiology, but this particular scanner it's funded by the hospital, but it's dedicated for research. So basically we have research that's commercially sponsored as well as investigator initiated. And that's mainly what I'm going to talk about today. So the majority of our requests in the department are for MRI research, but we do other types of research as well. It's a Siemens Prisma scanner with 80/20 gradients. We have a multi-nuclear option. On this particular scanner, we haven't done any non-proton work. On our previous scanner, we did some sodium work, and we have a full range of phased array coils. So this is what the suite looks like. That's the zone 4 room itself, and we have a number of coils you can see in the coil cupboard behind. The suite itself, on the left is the preparation room. So we do a lot of animal work here. So that's the prep room, and the doorway on the right is into the controller. And here is our setup. You can see we've got a projector on the side, an EEG set up in that little Faraday cage there. I'm not sure if I've got a pointer, but anyway. This is from inside the control room, so running an inhibition task from the control room, looking back that way. So we do a full range of studies. I'm not going to talk about more today because there isn't time. I'm going to focus on the first couple. I think Sarisha is talking about some liver work we're doing, and Kiri is later on talking about a study we're just about to start with real-time speech. So our longest collaborators for over 20 years is the Brain Dynamics Centre with Anthony Harris and Mayurish Kolgauka. We do a lot of functional imaging. We also collect diffusion tensor data, but we also, for the last 12 or more months, we've had a simultaneous EEG setup, so we can acquire simultaneous data while we're scanning and doing the functional tasks. So our focus there is on mental health. So we're doing a wide range of studies, some of the things that we've been doing previously, and also we focus a lot on depression. So these are just some of the papers that have come out recently with the work that we're doing there. And here's Mayuresh about to get the cap put on. This is a new 128 lead EEG cap, and here's Jingli with the cap already in position. Thank you for the photograph, Jingli. So yeah, so this work has been going on for 20, 25 years together with this group. And one of the other groups that I've had the pleasure of working with is here, the discipline of physio with Trudy Rebeck's group. We have done a large study using Megapress, which is a spectrally edited spectroscopy sequence looking at GABA and glutamate in chronic migraine and whiplash and low back pain patients as well. So this work has led to a number of publications, but also it led to the publication of some recommendations for performing Megapress at 3T, which is actually very technically challenging. It's a low signal to noise sequence, and the metabolites are overlaid with other larger metabolites, so it's difficult to get that data. Also some work with Kasia Kozlowska from the Children's Hospital. We've been working for a number of years with a group of functional neurological symptom disorder patients, and these patients are children and adolescents who have neurological symptoms that can't be explained by a disease process. So we've published with grey matter volumes. Resting state connectivity is something that we've been looking at more recently. And we've also used PRESS, which is the clinical spectroscopy acquisition sequence, and Megapress spectroscopy to investigate metabolic differences which are suggestive of dysfunction, neuronal dysfunction and transmitter dysfunction. So our first report actually, or the first report quantifying GABA in this condition has just come out a couple of weeks ago in Neuroimage Clinical, and that's some of the other work that we've published together. A couple of other studies just quickly, because I know time is passing. We've been working with Nadine Kasparian, who's now in Cincinnati, looking at parental buffering in children that have got congenital heart disease and looking at the way in which they respond when they're presented with images of medical equipment, which they've obviously been presented with a lot in their short lives. Also with Christy Griffiths from the Inside Out Institute, previously from Brain Dynamics. She looks at eating disorders, and she's been doing some fMRI work with her. She's also just had her engineers building a gustometer. And what is that, you may well ask? This is coming out to Westmead tomorrow afternoon. We're going to try to integrate that so that we can get patients or participants to actually choose a taste of some sort of food that they want to taste and see what happens in the reward system with those. And also with Geraldine O'Neill's group, looking at high-grade GBM to map the biochemical environment using a technique called magnetic resonance elastography to measure viscoelastic properties of the tumour bed of the tissue. So that's done by transmitting low-frequency shear waves, and those can be mapped, and that gives us a visual indicator of the tissue stiffness. This technique was invented for liver, to look at liver stiffness. Now, our animal work, just quickly, with James Chong and his group, we've had a number of studies over the last few years where we're looking at stem cells, platelet-derived growth factor, and the most recent study with spider venom, looking at regenerating the myocardium after an MI. We do structural and functional imaging. We've also got a research sequence that's from MGH looking at diffusion in the heart as well. So we've scanned over 150 animals with that work, and some of the studies, some of the papers have come out of it. That's the setup that we have for the pigs. As you can see, the ECG dots are quite central because the heart is located more centrally in these animals than it is in humans, and some of the imaging that we're getting out of the 3T clinical scanner. Pierre Kwan is also doing cardiac work, but in sheep. So we're looking at the effects of radiotherapy on the heart. So obviously radiotherapy is used to treat cancers, but it can also be effective in controlling VA. And so we're looking at the effects on MI scarred tissue. So some of the images and the setup for those patients as well. We have to often shear them a little on front and back, one to get the dots into position, but also they're quite large, so to get them into the scanner. And then the work with Gopi Rangan on polycystic kidney disease. So we actually did preclinical work on the clinical scanner using a clinical coil, looking at how the kidney growth could be effectively slowed, and also some vitamin D deficiency studies as well. That's the original group, A Blast from the Past, so I thought I'd include that photo. And some of the work that has come out of that. This is the setup. So that's a coil that we use for wrists and elbows in the back there. These animals were all between 200 and 300 grams, so they're quite small, and the imaging that we got out of the clinical scanner for that. And that went on to some human studies. So that led to an NH and MRC grant for the human study called PREVENT. And in that work, we were just looking at, very simply at prescribed versus usual water dose for patients with large kidneys with PKD. And anecdotally, a prescribed dose of water would slow the growth of the kidneys. And we found that actually was not true, but it had never been studied, never been proven before. Some of the work from that, and some of the work with Annette Hayworth's group, and Surisha is in the audience, the CBERT 1 and 2 studies, looking at personalised radiotherapy treatment based on quantitative multi-parametric MR imaging. So we did sequential imaging after radiotherapy to establish biomarkers. We also did some repeatability and reproducibility testing with Erin, with the Phantoms for her PhD work, and acquired across 3 different scanners, and then followed that up with the CBERT 2 study, which was basically looking at defining the spatiotemporal dynamics of hypoxia. So that was the same protocol, but no contrast agent and some of that. And I'd like to thank my team. I've got a fabulous team out at Westmead Hospital, and they make all of this work happen when I'm not on the ground as well. And our mascot, Kevin, and I'd also like to thank David Skerritt, who gives us an enormous amount of support for technical help. So thank you, and a quick whip around the world. I'm sorry if I spoke very quickly.
Thank you so much, Cheryl. It's a reminder that we are a university that spans many campuses. We have the Camperdown campus, we have the different hospitals affiliated with the university, and even private imaging facilities. So there's more to, there's a breadth to what we do, and there's a lot of activity and very interesting such out at Westmead. So thank you, Cheryl. Our next speaker is Roger Bourne. Welcome up, Roger. Speaking about forget about imaging. So welcome to the imaging conference and talk about forget about imaging. We're looking forward to that. Welcome, Roger.
The green button. The green button. It's not very often you get invited to a symposium to undermine what everyone else is talking about. But so I want to very quickly present some ideas about how an anthropocentric approach might be compromising what we're really trying to do in medical imaging. And I'll start with this. Whoa, what's going on? It's auto advancing. If we look at the history of imaging, it doesn't actually start with cave paintings. In fact, 500,000 years ago, people were making representations of their environment in 3D, but there was some sort of a conceptual breakthrough where they realized they could represent the 3D environment with a 2D drawing. And basically you could say that we've never looked back since then, but there's potentially some issues with that. So look at medical imaging. We know that radiologists are very good at what they do. They have a very complex visual analysis task. One example, if in screening mammography, is that it's been likened to a Where's Wally, only it has to be done in black and white. And the problem is not where's Wally, it's is Wally here today, and he's only there in 1 of every 200 images. So clearly radiologists are really good at what they do in that visual analysis task, but they're not perfect. Pathologists have a different kind of problem. They've got an image that theoretically contains a lot more information. It's in color and it has much higher spatial resolution. So they're solving a different visual analysis problem here, but they're also really good at that compared with the untrained observer. But it turns out that you can actually get a pigeon and show it histopathology images or mammography images, and it's just as accurate as the pathologists and the radiologists. But the issue there is not so much that pigeons are really smart or radiologists are dumb. It's probably that pigeons actually have evolved to do a task that is far more similar to this one that we're forcing humans to do here. And that's why we have things like double reading in breast screening, because we acknowledge the fallibility of the human visual perception here, but unfortunately it doubles the cost of that screening program. So we have also a lot of protocols now to try to deal with that inter and intra-reader variability that's a manifestation or a problem with human visual perception that we use in imaging. Okay, so I want to briefly look at the problems of visual perception. So one of them is we got a bad optical sensor. The processor that we use for that data that comes from that sensor has many, many problems with it. And I want to quickly look at some of these things here. So if you ever want an example of there is no intelligent design, just look at the eye. It's a really, really badly designed optical sensor where the wiring is in front of the sensors. The wiring goes in a big bundle through the middle of the sensor field. Many, many problems with this device, and it's made out of a really inhomogeneous material. It's got a variable contrast sensitivity that affects the sensitivity according to viewing distance. It's subject to optical illusions like this, not very good at understanding 3D space at all, and often it doesn't actually analyze all of the data that it's presented with. Here's an example of the eye tracking where you can see a large part of the field has not been investigated at all by the reader. So let's look at why we're actually doing imaging. It's to look at and characterize spatial relationships. In the case of medical imaging, we want to look at spatial relationships in human biology to characterize them and represent them. If you look at the history of medical imaging, Google search that, you'll always get something that starts with Röntgen. But in fact, 500 years before that, Mansell was producing two-dimensional drawings of biology. So we've got these 2D representations of biology, which are essentially what we're doing in medical imaging. And that's actually a problem. It's a two-dimensional tool being applied to what is actually a 3D problem. We don't really see in 3D. What we see is surfaces in an empty 3D space. And in fact, we're really, really bad at understanding things when, for example, here we see a lot of surfaces. The one thing there that isn't a surface, the rainbow, we don't really understand, and it's hard to interpret that. We only know what that is by having learned about it. Similarly with something like this, here we can't understand what this thing is except by a lot of inspection. The fact that the surfaces don't behave in the way that they normally do means it's very hard to understand the 3D properties of this thing here. And that's probably part of the fascination and the value of them, is that they play with our surface-based understanding of our environment. When we think about biology, all of biology is actually 3D. Biology cannot function on a 2D surface, a truly 2D surface, no matter what spatial scale you look at. And even when we produce representations like this here, we're producing a rotating surface view. And we have to do that because if it wasn't a rotating surface view here, our brain wouldn't actually be able to understand the complexity of the true 3D object here. We also have a really lossy analysis pathway. If we take our imaging system, which is basically a measurement device, we generally take a fraction of the raw data it produces, make an image out of that, and give it to this meat-based image analysis system that produces an interpretation at the end. And all through that process there, we're losing information that we acquired from the object that we originally analysed. What we do with radiomics is say that the human visual perception is flawed and compromised and non-ideal, but we don't deal with the rest of the information loss in this system here. We're just acknowledging one part of that problem there. We also have a really lossy learning and validation process. The example I give here is where the truth comes from histopathology. We take tissue samples, but because of the limitations of human visual perception in histopathology, only a tiny fraction of that truth data, the tissue that we've obtained, gets analysed. Another big loss of information there. We also have quite a lossy process in getting the information that the pathologist acquires back to the radiologist, who could learn from that truth data, if it were all available, to better interpret the original imaging data here. And unfortunately, we don't have any really reliable processes at the moment for assigning truth to the individual bits of information, the pixels in our medical images at the moment. Furthermore, we've actually got disease definitions that are based on human visual perception. So diseases based on histopathology are generally defined and graded according to hematoxylin and eosin staining, a stain that was developed 150 years ago and analysed with human visual perception. So what sort of definitions of disease might we have if we had different contrast mechanisms? Here's another visual light one, but if we weren't restricted to visual light-based contrast mechanisms, we might have completely different disease and truth definitions that we could use to inform our imaging or spatial characterization systems. So a few ideas about how we could be a bit less anthropocentric about what we're doing here. So one of them is just don't do the imaging at all. Take our spatial characterization data, take all of that data and analyze it. And we're close to the position technologically now where we can do that. And if we do this, we can develop a much better training system. We can analyze much more of the tissue. We won't be limited by how long it takes a histopathologist to work their way through the data. And we can have a far more efficient process of transferring that truth data back to the system that learns to interpret the spatial characterization data. That anthropocentrism is inherent also in the ways that we describe the technology we're developing in terms of intelligence, learning, vision, neural. We're often making technology that simply emulates human functions that isn't necessarily focused on the actual problems that we're trying to solve. There's things that humans are really good at that machines aren't, but if we take the humans away from the processes that they're not good at doing and give that to the machines, we can let the humans focus on the things that they're actually really good at, which includes making new machines. So my suggestion is we might progress our aims in medical imaging better if we don't think in terms of making images, if we get machines to do what we're really bad at, and we design them to do that and focus on our human behaviour. Thanks.
So before you leave, just thank you very much, Roger, for that philosophical sort of analysis. Are you saying, am I understanding correctly that you're just talking about not creating images and sending the machines to analyze the raw data, or not putting the person in the scanner at all? Just so I understand correctly. Please come to the
No, so there was scheduled to be a talk a few months ago from a English radiologist, I think he is, who's written a book about this. And I noticed in one excerpt, he said, one day we might get to the stage where we stop making images. But I think the machines that we make now that are called imaging systems are actually spatial characterization systems. Their purpose is not to make images, it's to tell us about the biology of the person that we're scanning. And the momentum that we get psychologically from calling them imaging systems potentially compromises the way we analyze the data. And the other question is, if we didn't think of these machines as imaging systems, perhaps we would design them differently. If we thought, what's the purpose of this machine? It's to characterize the biology, not to make images for people to look at.
Food for thought. Thank you very much, Roger. So Fernando, we don't need to buy any scanners. We're just going to go for the process. Our next speaker is Annette Hayworth. I'd like to invite her up. There we go. Tell us, Annette, about BERT. What is BERT? Annette's going to tell us about BERT. Not Bert and Ernie, just a different BERT.
Thanks very much. I'm going to start off by saying thanks to Roger for giving me a fantastic introduction to my presentation, because this is how we're going to use that spatial biology in practice. So that's worked out really well. Right, first on to, I'm just going to do radiotherapy 101 for those of you not sure exactly how we do things in the radiotherapy world. This is an example of a prostate cancer treatment that we would do normally. So the prostate, of course, sits hard in the pelvis. We're going to deliver a uniform dose of radiation to the entire prostate. We're going to bring our radiation beams in from lots of different directions, because what we're trying to do is make sure we don't over-irradiate our normal tissue. So basically, we're limited by the amount of radiation that we can put in the prostate due to the surrounding healthy tissue. So, as Roger said, let's throw out our imaging and let's just think of it in terms of producing something about the biology. And that's what we really want to do. So instead of looking at the prostate as just a blob that we want to put radiation in, why don't we instead see if I can get this laser pointer to work. No, I can't. Okay, so the red blob over on the right-hand side, that's part of a tumour. It's got a radio-resistant core, so it might be hypoxic. And what that basically means is that we need 2 to 3 times more radiation to sterilise the tumour cells in that part of the tumour, which is surrounded by the red line, compared to the rest of the tumour. Now, we do deliver radiation to the whole prostate because prostate cancer does tend to be multifocal. So we still want to mop up those stray cancer cells, but we probably don't need as much radiation in those bits of the prostate as we do in that hypoxic core. So the principle behind the BERT project, so BERT stands for Biologically Targeted Radiation Therapy, is we want to know where to deliver those really high doses of radiation. And also using quantitative imaging, we want to know how much radiation we need to deliver on a voxel-wise basis. So this is a tumour control probability equation. So what this tells us is that if we know something about the biology, and think of the prostate in terms of a voxelized structure, if we know something about the specific biology in each voxel, we can calculate for a given dose of D, and right in the middle of that equation you can see a little red D, that's D, the dose delivered to voxel I, we can calculate the tumour control probability. Now, what we know from radiotherapy is that if we increase the dose to the tumour, we increase the probability of curing the cancer. But also, of course, we increase the probability of causing complications. So the optimal TCP value is one where we maximise the tumour control probability but also minimise complications. And that tells us the value of little d in that equation at the top. Now, What this equation requires is knowledge of the biology. I won't go through all the details, but some of the things that I'll mention are potential doubling time or the aggressiveness of the tumour, the cell density, and if we've got hypoxia in there, we need to know about that because we need to put an extra bit of radiation in those volumes. So our question was, and as nicely put by Roger, can we use quantitative, perhaps I shouldn't use the word imaging, can we use that imaging data to inform this tumour control probability equation? So a few years back when I was working at the Peter MacCallum Cancer Centre, we recruited 70 patients who were scheduled to have their prostates surgically removed. So that provided us with some ground truth data. We also imaged the patients before they had their prostates removed. So we were able to co-register the histology with the imaging data and using machine learning techniques build predictive models. So those predictive models enable us for future patients to be able to map the spatial distribution of the tumour biology. And this is just a summary of some of the work that we've done in this space over the years. So we can define tumour location, tumour grade, cell density, and we've also found imaging features that can predict for hypoxia. So this is the work of Emily Herr, one of my previous PhD students. So she took this equation, she took those maps of spatial biology, she applied biological optimization techniques to produce a treatment plan. So in other words, we would use that to deliver the treatment to the patients. So what we see here is a conventional plan. So this is just one prostate cancer patient that she took. She retrospectively calculated the tumour control probability and it came out with a value of 0.61. She then re-optimised the dose distribution using the biologically optimised approach, and she was able to show that the tumour control probability increased up to 0.84, so quite a considerable increase. If you look at the little pink circle below the prostate, that's intended to be the rectum. You can see on the left, there's more, so that dark red area, so the rectum's getting more dose than on the right. So not only increasing tumour control, but also decreasing probability of complications to the rectum. So far, I've talked about what we would do, take a new patient in, quantitative imaging, and then deliver the treatment. So what I'm going to talk about now is what we do after treatment. So Cheryl mentioned this in her presentation as well. So if we start off before treatment with a map of the tumour biology, can we image patients after treatment to see whether the tumour is fully responding to the radiation dose? So this is the work of Erin Wang, who finished her PhD I think last year, is now working with me as a postdoc. So in AIM3, the main goal was for us to identify quantitative imaging features that would predict for treatment response. But actually, Erin spent a lot of time looking at the uncertainty in measuring those parameters. So what she wanted to know is, are any of those parameters actually reliable in predicting treatment response? So this is just one of the studies that she did. She had a group of healthy volunteers, which she imaged over several weeks. She also had a group of patients that were imaged at 2 time points before they had radiotherapy. So she could map the uncertainty specifically in the tumour compared to the volunteers, which is just benign tissue. So Erin measured the repeatability coefficient. So the concept here is if you image the patient before treatment, then you image them again after treatment. If the change is larger than the uncertainty or the repeatability coefficient, then it's considered a reliable or a detectable parameter. So we ran a couple of studies during her PhD. The first one was CBERT-1, where we imaged before treatment and at 6, 12 and 18 months after treatment. There was a second study, which I won't talk about today. So we imaged the patients, T2, diffusion-weighted imaging, DCE, and bold imaging as well. Erin calculated the parametric and pharmacokinetic maps, and she's also continuing on with doing a radiomics study. I just wanted to briefly mention IVIM, or intravoxel incoherent motion. This is some modelling that we're sort of pursuing at the moment. So this is intended to give us some idea of whether the tumour has got hypoxic volumes. I won't go into the details, but there's a number of parameters that you can pull out of this. One of those being HS, the hypoxia score, which is an overarching measure of probability of containing hypoxia. So this again is very high level summary of Erin's work. In the left column, you've got the pre-radiotherapy scans. I've got T2 at the top, I've got ADC in the middle, K-trans on the bottom, and of course there's multiple more parameters which I'm not showing here. The next column is 6 months post-treatment, and the final column is 12 months post-treatment. Now, the darker shading in the 6 months, you can see the lighter shading is where the original tumour was. The darker regions is where those voxels have passed that threshold for being detectable. So it increases the volume, the number of voxels increases at 12 months. The thing to see, though, is that the pattern of the voxels that are detected are different in ADC as they are to K-trans. And obviously, they've got those other parameters as well. So what we're looking for here are those voxels that haven't passed that threshold, and those across all of the different parameters, and those would be the ones that we would be worried about to indicate lack of treatment response. So what Erin found was a combination of parameters is needed, but it does show a promise for predicting tumour response. And we found K-trans and VE from DCE to be the most reliable, and also the hypoxia score from the IVIM modelling. So this is the conclusion then. So I've shown you that quantitative imaging can be used in the treatment planning stage, but also we're continuing our investigations in looking at using quantitative parameters for measuring treatment response. What we're hoping now is that we've got enough evidence to say we need to put this into clinical trials. So future prostate cancer studies, radiotherapy studies should be imaging at multiple time points so that we can correlate those parameters with actual true treatment outcomes. So I'd just like to thank the many people who have been involved in all the projects over the years and our funding partners. Thank you.
Thank you so much, and I was so happy to see Bert there at the end as well. Thank you. As I invite up Steve Meikle as the next speaker, we've formally transitioned between session 1 and session 2. I don't know if you noticed it, but let's take 30 seconds and everybody just stand up and get a little bit of a stretch, if you would. Those of you online can join in your virtual space as well. We're not going anywhere. We're not leaving the room. We're just standing up. And then we're going to be sitting down also. So please come and have a seat again.
Ready to go? Okay. All right. Well, it's very nice to join you this morning. Thanks, Martin. As the title says, we're often running, although I think it would be more accurate to say, like Ellie in the photo here on the right, that we're often walking. But we're underway. That's the most important thing with this new facility, which Fernando already mentioned. So it's the Australian National Total Body PET facility. And it's a partnership, as Fernando mentioned, between the university, the Northern Sydney LHD and NIF. It has this 50-50 timeshare model where we split the capacity of this system 50% for clinical work and 50% for research. It's been operational since August of last year, and the official launch was on the 12th of December. And you can see this photo of the ribbon cutting with all the important people at the front there and all the people who do the work at the back. As Fernando already mentioned, we ran a research symposium in conjunction with that launch. So in this talk, I'm not going to talk about the technology. I've done that in previous talks. But if you want to know a little more about how total body PET works and its potential future clinical applications, that's the QR code that Fernando also showed, and I'm happy to share the link with you in the break as well. What I will do is just give you a bit of an outline, a bit of a snapshot of the projects that are underway on this facility. And then I'll talk in a little more detail about my own projects. But as you can see from the dashboard at the top of the screen there, we have quite a variety of projects in various stages of progress, including a couple of international and interstate projects. And then what I've done here in this list, I don't expect you to read all these projects. It's just to give you a flavour for the variety and range of disciplines and fields that these projects cover, which are indicated by these little icons. So we have projects in drug discovery, neuroscience, cardiovascular, pediatrics, a couple of data science and engineering projects that Yorgos and I are involved in, and heat health. So quite a variety. And for the rest of the talk, I'm just going to talk a little bit about our own research and the plans for what we're just starting to get started with. And the focus of our research is on whole body dynamics. So a little bit sort of riffing on the theme that Roger introduced, where what we're really interested in is establishing and extracting information about the not just the spatial characteristics, but the spatio-temporal characteristics of the data that the system can produce. So just to explain what I mean by dynamics, in a normal clinical total body PET scan, we would inject the patient when they're outside of the scanner, leave them in that room for up to about an hour, allowing the radiopharmaceutical to reach equilibrium in all the tissues of the body. And then we'd put them on the scanner and take an image for typically 5 minutes. With dynamics, instead of doing that, we inject the patient while they're in the scanner and we collect data continuously. And that gives us really useful information about the spatio-temporal changes of the radiopharmaceutical uptake in different tissues. And so we get information about the uptake, the retention and the clearance of the tracer from all of those tissues. Now, why would we want to do that? So the reason is, and I think this case study illustrates it very nicely, is there's potentially really useful clinical information in this the dynamic data. So this is a study that was published from Turku in Finland, publishing a whole range of case studies where they did dynamic scanning. And this is a patient who was scanned with FDG. This is the standard clinical standardized uptake value image. It's a patient with a lesion, a cancer lesion in the mediastinum there, so you can see the abnormally high uptake of FDG. But you also see this uptake in the axillary lymph node, and that's a common thing that the clinicians see in patients who are undergoing immunotherapy. And the question is does that increased uptake of FDG in the lymph node represent metastatic spread of the cancer to that lymph node, or is it just a flare response to the immunotherapy? When you look at the dynamic data, you can use some of the techniques I'm going to talk about in a moment to separate out the metabolic part of the signal, which is shown in the image in the middle, from the rest of the signal, which is shown on the right. We call that the distribution volume. And what you see in this particular case is that uptake in the lymph node has completely disappeared from the metabolic part of the signal. So you can conclude from this that it is not metastatic spread. It is actually a flare response to the immunotherapy. But normally the clinicians don't have this information available to them. So how do we extract that information? Well, there are some traditional techniques like compartmental modelling. So in this particular case, I'm showing here, this is a 2-tissue compartment model, which is a very well-studied, well-validated model for the brain with FDG PET. And normally, to analyse the data using this model, you would need arterial blood samples taken throughout the PET scan. But of course, with total body PET, we always have the heart in the field of view, so we don't have to do that. So we have a nice non-invasive way to collect the data that we need. And from that data and from the model and least squares fitting, we can calculate a parametric map like the one on the right here. This is called the KI map, and it represents that metabolic part of the signal that I showed just a moment ago. The problem, however, is that model, although it's very well validated for the brain, it's almost certainly the wrong model to use in the liver and in other tissues such as the gut. And so most of our techniques rely on just the use of a single a priori model to apply to all the tissues in our data. And the question is, which model should we use? One model won't fit all of the data here. So for one solution that we've been working on a lot in my group is a method we call PET-ABC, which is based on Bayesian computation. And it has two nice features. Firstly, it's able to handle multiple models in one data set, and it selects the most probable model, the most suitable model, a posteriori based on the data. And secondly, it can also give us information about the parameter uncertainty. So I won't go into the details of the method, but one other feature is it's being based on Bayes' rule means that we can incorporate prior information into the model as well. So we may have prior information about both the model and the model parameters. And then this is a result produced by my honours student Alistair, who's sitting here in the audience. And it's based on previous work that my former PhD student Gail did. And what this is a probabilistic parametric map based on this PET-ABC method, which shows the relative probability of two competing models, Model 1 and Model 2, where Model 1, I've got my glasses on, is the one where the voxels are showing up in red that indicates irreversible kinetics, K4 equals 0. And the voxels in blue are those which are more suited to the second model, which accounts for reversible kinetics. So just to illustrate that we can analyse these really rich spatiotemporal data on a voxel by voxel basis and yield interesting, useful information. The other challenge we're interested in addressing is just the sheer volume of the data. So this schematic shows the overall pipeline from going from acquired data to these parametric images. And we generate up to 1 terabyte of data with each one of these studies. It can take 4 hours to reconstruct the data and generate up to 4 billion data points that have to be fit. So this is a very, very computationally demanding task. And so it won't surprise you that we're going to throw deep learning at this problem, or at least explore where deep learning best suits this problem and can help. And in fact, in this ARC grant, which we've really just started, it's also about combining that previous technique I just described, the Bayesian technique, with deep learning and seeing how well we can generate accurate, reliable parameters efficiently. The third challenge I'll just touch on is to do with understanding how these different signals from different parts of the body actually relate to each other temporally. And we think that there are applications around the understanding the signalling between the brain and other organs that total body PET could potentially help with. So for example, there's a lot of interest in the signalling between the brain and the gut axis, and it's thought that that signalling can influence the progression of Parkinson's disease, for example. And there's also competing hypotheses about the actual origin of the disease in motor neuron disease, whether it actually begins in the brain or whether it's in fact a pathology that starts in the neuromuscular junction. So in both of those cases, understanding how signalling between different parts of the body works could be really useful. And this is just a schematic to give you leave you with a bit of a teaser. So this is kind of another concept that we're developing, which is whole body connectivity. We're not the only ones to propose this, of course, but our unique take on it is that we're going to look at neurotransmitter signals as well as metabolic signals. And so what we are proposing to do is to measure the release of neurotransmitter in individual voxels. So we have modelling techniques that can do that. We're using dopamine as our model neurotransmitter. And from that data, we can put together a connectivity map, a lot like what is done in fMRI and structural MRI. And from that, we can do an analysis of the key signalling pathways using network-based statistics. So that's just a little bit of a teaser, and hopefully we'll have some data to present in the future on that. So with that, I'll leave you with my acknowledgements, and thank you for listening.
I might ask you a question before you step down, Steve. So the difference between the metabolic activity and the distribution volume was really interesting there.
Yeah.
How far would that be from clinical use in your view?
Yeah, that's a very good question, Martin. So there's a lot of different groups that are working on ways to take that methodology and make it clinically practical. The biggest challenge there that I didn't mention, but we're discussing a lot with Dale and others, is that requires the patient to be in the scanner for an hour, and that's not really practical clinically. So, so there's challenges on the sort of the technical side of things in how you extract that useful information, but there's also some really practical challenges that we're going to have to address. But the scanning time is a big obstacle to translating this clinically.
Thanks for that insight, Steve. Moving on, I am the next speaker. So I've shared my screen now. If the AB would switch over that, there we go. And I'm going to be talking about a new thing that you may or may not have heard about. It's called the National Imaging Database Australia, NIDA, not to be confused with the National Institute for Dramatic Arts in Sydney, but the National Imaging Database Australia. Let me tell you a little bit about that. So what is it? So NIDA is a research framework for extracting imaging report text from the radiological information system. So any participating entity, whether it be a department of radiology in a hospital or an imaging private imaging facility that wishes to participate, can contribute with the reports, so the text of the imaging reports, and then linking those reports with the identities of the individuals to outcomes data, like the National Death Index, the Medicare and Pharmaceutical Benefits Schemes, ICD-10 codes, and DRG billing codes. And the thought process behind this is it leverages the existing National Echo Database Australia, NEDA infrastructure, and I'll get a little bit into that on a subsequent slide. But importantly, the existing infrastructure that NEDA has put into place makes research, it lowers the barrier to entry for research on a large scale. Firstly, it asks for a retrospective waiver of consent to go back and extract data for patients that have already been imaged for clinical indications. But then it has an interesting mechanism of a prospective continued enrollment with an opt-out consent. So each person who comes for, in the case of NEDA, a clinical echocardiogram, they get a business card as they leave the room and said, you're going to be included in this data unless you want to not be included. And on that business card is a QR code and a URL where they can read more about it and opt out. And if they don't opt out within 2 weeks, they're in. And that leads to an enrollment rate in excess of 99.5%. So it's a very low opt-out rate, which is ethically approved and justifiable considering the low intrusiveness of the interrogation and the research. And what's really interesting and as probably one of the key drivers to this behind the primary analyses is this last bit of a catch-all ethics for site-specific or national image analysis projects. So this is the trick, so to speak, and we're not trying to trick anybody, but the primary data is the reports. But in participating in this retrospectively and prospectively, there is approval to extract images. It would be too much to, let's say, on a millions and millions of patients' images scale, extract every image and replicate it in a research PACS for the entire country of Australia. But we at least have the ethics framework to allow for example, extraction of a couple hundred or a couple thousand across multiple sites or at one site. Or on a very simple level, the radiologist in training being able to go back and look at the past 100 scans of a certain type with a certain question and interrogate that for research purposes and be able to publish it with an existing ethical framework. So this catch-all ethics is an attractive feature that has direct implications for the clinical imaging research capacity that we have within skin, but of course on a national scale for participating centers as well. So just to talk a little bit about the primary objective, which justifies this, let's call it research grab of data, it's to establish and describe the relative strength of association between multimodal, multi-organ imaging and clinical outcomes. A very broad thing. We can say that, for example, it's more dangerous to have a pulmonary embolism on a CT pulmonary angiogram than it is to have a broken kneecap on a plain film X-ray. But how does that relate to having a stroke on the brain MRI or a cancer on the FDG PET with a lung cancer, for example? So we can establish the relationship between imaging phenotype and outcomes on a comparative basis on a broad scale. In addition to that, there's sort of infrastructure goals. One, to create a highly secure, fully virtual database of identified patient data, which then is inaccessible to external users, but is used to create the linkage. So in order to do linkage, you have to have patient identifiers, but you can't give patient identifiers to individual researchers, but you can do it in a secure and approved environment. And then secondly, to create this highly secure, fully virtual analysis server that will be used to authorize users for data analysis of imaging data and others' data that can be linked. So both linkage, not accessible to researchers, and then finally de-identified linked data accessible to researchers in order to achieve the primary goal. But you can imagine then the secondary goals, like identifying the strength of association between imaging findings and antecedents, correlates, or comorbidities associated with clinical outcomes, or associations with measurement data from image analysis and clinical outcomes, or epidemiological and prevalence studies of different conditions or suspected conditions imaged by different modalities, or examining the association between risk factors, biomarkers, and the presence of disease identified by imaging. So this is all sort of a lofty ambition within the framework of NIDA. Now, going back to what they did with NEDA, the National Echo Database on which this is built, just to give an example, the current data in NEDA is 1.4 million echo studies from over 800,000 patients with 35 sites, and it's very soon going up to 2 million studies from 1.3 million patients from 45 sites, and getting linkage not just to National Death Index, which it's currently, but also to the MBS, PBS, ICD-10, and DRG codes, so the diagnosis codes, pharmaceutical treatments, and their billing codes. And this has led to an excess of 40 publications over the past roughly 8 years, many in the high-impact cardiovascular journals. And these are the sheer scale combined with the linkage with outcomes has made it possible to identify things like, for example, that arguably the biggest finding from NEDA is that you don't need to have severe stenosis in your aortic valve. It's enough to have moderate stenosis of your aortic valve, and it's still really, really bad for you. You're the survival with moderate aortic stenosis is just as bad as severe, which has led to a number of prospective trials running now where they're randomizing to aortic valve replacement or repair in people with only moderate aortic stenosis, and ultimately trying to increase survival in cardiovascular disease. So how does this work? Well, what NEDA did was they created an organization which has now been renamed to the Clinical Imaging Research Institute, which is a not-for-profit research company limited by guarantee. And this is a slightly atypical way that we do research. We've always done our research within the realms of the university. But for the purposes of creating NEDA, they wanted to make sure that nobody felt that they were being sort of tricked into supporting one organization over another. So they created sort of a Switzerland, if you will, a neutral ground entity in a new corporate entity. So a new ABN and a new organization. Now there's no physical building; it's a sort of a virtual organization. But within what was originally called NEDA and now is called SIRI, there is the technical infrastructure and the know-how. So there's an engineering team that has the experience with handling these larger, or let's call them very large data sizes, and performing those linkages, working with the different linkaging organizations to accomplish this and make it available to researchers. So NEDA, as in the dark blue, is something that exists. There's a steering committee for that. But then the ambition is to create NIDA, which is for the all imaging, all organs, with its own steering committee, but then also have each particular things of interest. So for example, cardiovascular magnetic resonance, have one group just for that, one for cardiovascular CT, one for ECG, one for nuclear medicine imaging in the cardiovascular space. But you can imagine a steering committee for each of your organs of interest, or maybe even your diseases of interest. So this is something that's on the upswing now. We don't have it established just yet. The NIDA infrastructure, the SIRI infrastructure exists, NEDA exists, and the technical platform exists. But the current stage is that we've gotten seed funding to have a NIDA coordinator. That's Dr. Enid Eslick, who's now a senior lecturer with us at the university. She has a background in medical physics and nuclear medicine imaging. And she is working on the study protocol, which is soon to be circulated to key opinion leaders and stakeholders in the field nationally to get sort of on board for an application for ethics approval. So in the near future, we'll be submitting for ethics and governance and seeking funding. But I just wanted to mention this to you all, that NIDA is something that's sort of happening, and it will hopefully lower the barrier to entry for clinical research in the clinical research environments for participating sites. And when I say participating sites, anyone that wants to participate, because it's basically a copy paste of their radiological information, so the RIS reports that would go into NIDA, and then the linkage would be sorted out by NIDA. Of course, there would be local ethics and governance approval applicable, but we would have an existing central ethics approval, which we're now seeking. So that was shortly about NIDA. While I ask Luping Xu to come up as the next speaker, I might open for questions if anyone has any questions about NIDA while we're thinking about that. You might not have one now, and you're welcome to reach out in the break. Go ahead, Fernando, you can speak loudly and I'll repeat your question into the microphone. Absolutely. That's the expectation. The question was, do we expect that the opt-out would be accepted? Well, we have the opt-out existing running in the echo space, and it's just echo is an imaging clinical thing that we do, and we're applying to the same ethics committee that has already approved NEDA for when we want seeking NIDA. But yeah. Some cardiologists would disagree because we have our relationship to the echo and being able to identify. But yeah, absolutely, there might be identification issues there, and we'll have to deal with that as we go. But that's certainly our ambition to get opt-out from the beginning. Yeah. And with that, welcome up, Ping. Are you going to use? Yeah. Okay. I'll stop sharing there. Stop sharing. Okay, and thank you for that.
So that's this one. Okay, yeah, so firstly, a short about me. So I'm from the Faculty of Engineering with a different background. So I work on the intersection of medical image analysis, machine learning, and computer vision across different semantic levels,
including the medical image synthesis, segmentation, and classification. And today I will share my recent research focus on a relatively new topic for radiographic report generation, known as R2Gen, and an associated task known as medical visual question answering. And first, let's focus on R2Gen. So the exponential growth of radiographic imaging data exceeds the supply of trained readers, leading to overwhelming workload for radiologists, especially in public sectors. And the increasing volume and complexity of cases contribute to the reading fatigue and the diagnostic errors. So this calls for the automated generation of radiographic reports to reduce the workload, mitigate the diagnostic errors, and speed up the clinical workflow. And the R2Gen task is an AI task to generate text-based reports to describe the visual findings about a medical image. And the typical radiographic report consists of two parts. The impression part is a one-sentence summary about the image, and then the findings part provides more detailed explanation about the observations. And this task is challenging because we need to capture and narrate fine-grained visual differences of clinical importance among many similar medical images. And we also need to address the data bias where the disease-related words may be overshadowed by the common image content. And we also need to generate long and detailed paragraph to report our findings. In the following, I will detail how we address these challenges in developing R2Gen models. Okay, so in the first work, we introduced a self-boosting framework to learn highly correlated image and text features so that the generated report could capture the subtle but critical visual changes in images. So this is achieved by explicitly aligning image and text features through an auxiliary task known as image text matching. So this task tells whether a given pair of image and text is a true match. And the text image matching and report generation are built as two branches of our deep learning model, and they are jointly trained through our proposed self-boosted triple laws to boost mutual performance. And to facilitate the generation of long text, we adopt a hierarchical LSTM model for the report decoder. So a sentence LSTM model will generate the sentence topic, and a word LSTM model will produce the report word by word. So, and our model was validated on 3 public benchmarks, and here are some examples. So here, this red color indicates inaccurate, incorrect generation, and this blue color indicates inexact generation with similar meaning. And the green color indicates a generation exactly matching the ground truth. And our model performs well across many evaluation metrics commonly used in natural language processing. And our advantages on this CIDR matrix, which is the last column, is more pronounced. So this is a positive sign because this CIDR matrix focuses on the key information by downweighting the common words across all reports. And then in the second piece of work, we leverage the transformer model's ability to capture the long-range dependencies among both image regions and sentence words for R2Gen. So here we propose a pure transformer-based architecture. We use the vision transformer model as the image encoder and the memory-driven transformer model as the report decoder for long paragraph generation. And our model is supervised by multi-criteria, including the image text matching and a multi-disease classification model to capture the disease-related information, and term importance weighting to capture the less frequent but critical keywords in the report. And this model is further extended. So we replace the image text matching task by a well pre-trained clip model, and we propose new attention blocks to better associate image and text features. And we also jointly train the medical concept prediction with the report generation. So we propose to use this red graph to extract more than 700 medical concepts, and they are more fine-grained medical texts compared with the dozens of medical texts used in the existing R2Gen models. And here in this work, we capture the fine-grained visual differences, visual patterns from a different perspective. So we know due to the fine-grained nature of medical images, focusing on the correct image regions while generating the reports could be quite challenging. So inspired by the multi-specialist consultation scenario in clinics for the challenging diagnostic cases, we propose this ME transformer to emulate the multi-specialist joint diagnosis scenario. And our model introduced multiple learnable expert tokens, so which are these red tokens in the graph, and then into the transformer encoder and decoder. So then in the encoder, each expert token collaborates with other experts to focus on different image regions, providing complementary information via orthogonal laws to minimize their overlap. And then in the transformer decoder, each expert token contributes to a candidate report. And then the final report is determined through an expert voting strategy. So our model performs well on the NLP-based matrix as well as the clinic scores. And here we also, on the left here, we visualize the image regions mostly attended by the learned expert tokens. So we can see that each expert token attend to a distinct but critical image regions to provide complementary information. And on the right, we visualize the image text attention map here. So our model can better align the locations with the relevant text. So here in this example, the ground truth report mentioned about the cardiomegaly here. And our model successfully captured this anomaly, but the baseline model in comparison failed to do this. So this is consistent with the observation that our model actually can better attend to the heart region, which is the last column, compared with the baseline model. Okay, so after introducing this R2Gen, I now move to this medical visual question answering. So for a given image and a text question about the image, so this medical VQA aims to automatically generate text-based answers. So, and through this question and answering process, this medical VQA could provide a user-friendly way to support clinic decision. So the questions in medical VQA could be either closed-end, such as the yes/no questions, or open-end, such as the WH questions. And while existing methods often treat this medical VQA as a classification task and perform well on the closed-end questions, they struggle for the open-end question. And some methods use the generation-based models to improve the open-end question. However, they tend to generate many non-existent answers, leading to low accuracies. So to address these limitations, we propose our Q2A transformer to leverage both strengths for a unified treatment of different question types. And our model could improve the answers to both the closed-end and the open-end questions, while we achieve a more significant improvement on the open-end questions as indicated here. So these are the examples of the generated answers, and we also visualize the model attention for sanity check. So TNL have introduced our works before the recent emerging of large language models. And the remarkable power of large language models, such as ChatGPT, suggests their potential beneficial for this R2Gen task. So recently we published our first attempt called R2Gen GPT, so to integrate frozen LLM for the R2Gen. So we propose 3 different models with different levels of trainable parameters to connect image modalities with these large language models. And our models achieve close to the SOTA performance by only training a lightweight visual alignment module with the frozen LLM. And our code has been shared on GitHub. And we also conducted a comprehensive evaluation on the recently released GPT-4 We tested its capacities across diverse medical imaging tasks, including R2Gen, medical VQA, and a task called medical visual grounding. So this is to locate the text-referred regions in the image. So we used the quantitative analysis, human evaluation, and case studies for extensive evaluation. And we found that GPT-4 is good at understanding medical images. It can generate high-quality radiographic reports and answer the questions. However, it has to be substantially improved for this medical visual grounding task. And we also point out the limitations of the current used NLP matrix in evaluating the performance of large language models and suggesting the necessity of developing new evaluation matrix. So, and that concludes my presentation today, and I would like to thank my collaborators and students for their unconditional support during this research adventure. Thank you.
I might ask a question of you, Luping.
Yes.
So, in the medical field,
Yeah.
we typically ask ourselves the question about a colleague: would I send my relative to this colleague for a medical consultation as a sort of a quality metric of trust? Would you send a relative of yours to your own report generator?
Okay, certainly not now. Yeah, so I have to acknowledge that the performance of the model has to be significantly improved. Yeah, because currently all these models are trained based on the guidance of the traditional natural language-based perspective, right? From the perspective of natural language processing, not especially from the medical perspective. So that's why actually at the end, I point out the importance of developing some evaluation metric and maybe also the supervision from the medical perspective, right? So we can more accurately evaluate the quality of this report generation from the clinic perspective rather than the natural language processing. Yeah.
Thank you very much, Luping. So just a little bit of a summary of what we've seen so far. We started off by hearing a little bit of an update on the network. Fernando Calamante told us about the developments and status of the Sydney Imaging research imaging infrastructure. Ryan Sullivan told us about the research analysis capacity and the features and services available through the university and nationally. Cheryl Foster told us about the capacity and projects going on out in Westmead, and Roger Bourne challenged us to forget imaging all in all. Then Annette Hayworth introduced us to BERT, the biologically relevant imaging related to radiotherapy. Steve Meikle gave us an update on the total body PET, is often walking, and the capabilities and potential therein. I touched upon the National Imaging Database Australia, NIDA, project that's emerging. And now we heard about from Luping Zhu automatic report generation. So that got me excited. I was pretty packed program there. Now we have morning tea rounding off at 11 a.m. and we're going to go then into the research showcase, which on the one hand showcases research, but also has a competition component for the best EMCR speakers. You'll see the beautiful research showcase best speaker prizes up on display there. The research showcase is a combination of EMCRs, HDR students, as well as seasoned professors like our first speaker, Kazuaki Negishi. Kaz, are you, where was Kaz? If you would come up and start making your way to the front. We're waiting for him to do that shortly. Also, we have, do we have the first slide with the QR code to put up? There we go. Yeah, that's the first presentation. Do we have the QR code slide? The one before that? No, we don't. Okay, I'll tell you then, at the end of the presentations, you will all be given an opportunity to vote. So we have hidden among the audience judges of the EMCR presenters, and they will be judging you all, speakers that is, and then at the end, all the audience will be given the opportunity to vote, and the judges will take the audience's vote into account and consolidate that into the final decision. We have the 3 prizes, the 2 finalists, and 1 winner for the EMCR research presentation. And without further ado, we have a tight schedule, which I'm going to be keeping the time for. And we have the first speaker, Kazuaki Negishi. You will have 3 minutes to give your presentation. Welcome, Professor Negishi.
Thanks, Martin. Hi, everyone. I'm not the EMCR, unfortunately, so that's no board for me. Okay, so here. So those who do not know me, I'm from Nepean Hospital, cardiologist by training. These are my research portfolio, but I will go through. This talk is about heart attack. So then when patient develop chest pain, they call ambulance. We do some tests, we give some medications. Then patient come to the hospital, we put the stent in, open the blocked arteries, so we are happy wish. So the issue here is the three limitations of current practice. Number one is we can only salvage 43% of the myocardium at risk, which is less than half, obviously. And even in the successful primary PCI or stent procedure, more than half of the population has the very, very severe form of microvascular damages. We call it microvascular obstruction. And then lastly, we have to wait patient to come to the hospital. These are three limitations. Lots of people globally worked on this, all neutral or negative but one. So this is our approach. We use the imaging technique. We have been using this technique for more than 2 decades for the diagnostic purpose, but now we move to the therapeutic era using this as a therapy to reduce the infarct size of the heart attack. So how we do that, and there's a bunch of in vitro, in vivo data. This is the first RCT in humans from Brazil. They showed they can reduce the infarct when we apply this clinically into the humans, along with the stent procedure. So what we did in the Nepean Hospital in the farther west here, we did a similar trial, but slightly different manner. We at the second arm in the middle, we did the, before and after the stent procedure, they did it. We did one arm just only after the PCI, and then see what would be the best way to apply this to just finesse the protocol a bit. So this is our result. Because of COVID, we have to stop it early. But as you can see here, there was, in the green ones, has smaller infarct size. It's not statistically significant if we do the group comparison, but there was a trend. More importantly, with a bit of surprise, myocardial salvage index was significantly better in the green one, which one has the before and after the stent procedure. Orange one had only post, which means if we compare green versus orange, we see the importance of the prayer. So now we move to the clinical trial here in 3 hospitals in New South Wales, and we were waiting for the data. So our future view is we apply this into the ambulance, and we were going to tackle this outside of the hospital. Thank you very much.
So that was fantastic for keeping the time, especially. But what do you see as the biggest challenges in this kind of a study? Is it the logistics of making it happen, or is it the imaging evaluation and the logistics for that? What do you see the biggest challenges?
So biggest challenge is the time constraint, which is the logistics. To squeeze, we have only 5 minutes before the stent procedure because time is muscle. Every minute counts, so that's the most difficult part, but we will do that.
Thank you very much. And the next speaker is Chandrama Sengupta. Welcome up, Chandrama, to give your talk. Chandrama. Ready, set, go.
Well, so where do I change the slides? Okay, well, good morning, everyone. And I'm going to talk about our research on developing a tumor tracking technology in liver radiotherapy and its bench to bedside translation in a clinical trial. So to start with, what is radiation therapy? So in radiation therapy, we deliver this high energy radiation dose to the tumor, aiming to kill all the cancer cells. Now, one of the main constraints in delivering precise radiation dose to the tumor is that the tumors move during treatment due to the breathing motion, cardiac motion, and a number of other types of motion. And it could be up to 3 to 4 centimeters at any time point. And so why that is a problem? So say if the tumor moves during treatment and you have a static radiation beam, then we would miss the target. If we make the beam larger, that means more radiation dose to the healthy tissues. That means more toxicity and side effects in patients.
So what we really want to do is track this tumor as we deliver this high energy radiation beam to the tumor and correct for any motion. But unfortunately, there's no solution that works on standard radiotherapy systems. And this is where our research comes in. So we have developed a technology called kilovoltage interfraction monitoring, or KIM. So what it does is, as we deliver this high radiation beam to the tumor, it also at the same time images the patient using the kilovoltage X-ray images, and then segments the tumor in the X-ray images, and then doing some more mathematics, we get the tumor translation and rotation during treatment. So for its clinical use, we have developed this software. So this is a video. So you can see that the images here are coming in. It's being segmented as we are treating the patient, and at the bottom panel, you can see the tumor motion being displayed. And also there's an action threshold for the clinical team. The continue means the motion is within threshold. If there's a warning, that means the motion is outside the tolerance. So this method has been commissioned at 7 hospitals in Australia in the LARC trial. So the LARC trial is the liver radiotherapy with KIM guidance, and we have treated 32 liver cancer patients so far. So the main takeaway message from this trial is that analyzing the data from all these 32 patients, KIM could target the cancer with sub-millimeter accuracy. If we compare that with, say, the standard of care treatment, a motion of 4 centimeter, there's no knowledge where the tumor is, but with this method, now we know where the tumor is. And also because it's a software solution, we can implement that at any center. So we recently published a first in-human paper in the Radiotherapy and Oncology Journal. So if you want more information, have a look there. And I'll stop here with these pictures. So the KIM technology being used at a number of centers across Australia, and you can see the involvement of the clinical team there. That's all, and thanks very much for listening.
So thank you so much for that presentation, Chandra. In the world of changing things, there's the technical problem of fundamental physics, and then there's the engineering implementation.
Yeah.
What would you say is the bigger challenge here for making this happen?
I think for us in general, one of the biggest challenge was the patient recruitment in the trial. I think one of the factors was the pandemic, but in general, recruiting patients and getting the clinical team trained to do this, this has to happen in real time. I think that was one of the biggest challenges.
But the technical aspect, was it an engineering challenge or a physics challenge to make it?
I think it's both physics and engineering. So there's some mathematical optimization that has to be done in sort of at a very within a fraction of time. So I think there was mathematical and engineering both.
Congratulations, man. Great work. Thanks. And welcome up Marshall Dalton, our next speaker. Can we jump to that slide? There we go. Are you ready, Marshall? On your mark. Get set, go.
All right. Hello, everybody. So I'm just going to go through some neuroimaging work that we have been doing to look at the relationship between structural and functional connectivity of a brain structure called the hippocampus. So the hippocampus is located deep in the medial temporal lobe of the brain. And there's long-standing agreement that it's important for different aspects of memory processing, and it's affected in different diseases like Alzheimer's disease, schizophrenia, resulting in memory impairments. Recent advances in neuroimaging have allowed us to look at this structure in much more detail over the last decade or so. And in relation to functional imaging investigations, we know that the hippocampus, different parts of the hippocampus are involved in different aspects of cognition. And we've also developed these really detailed methods to look at how different parts of the hippocampus anatomically connect with other parts of the brain. But the problem is these different streams of structural and functional research have generally been done separately, and we have surprisingly limited knowledge of the relationship between structural and functional connectivity of this structure. So we aimed to address this gap by assessing how structural connectivity of the hippocampus relates to its functional complexity. We did this using data from the Human Connectome project, and we essentially had a four-step approach to our analysis. So we first developed a tailored pipeline that allowed us to isolate the white matter pathways that directly connect the hippocampus with the rest of the brain. And we took this data over and applied it using track-weighted dynamic functional connectivity that essentially allows us to transfer the functional data at the end point of each track to the track itself, and allows us to create these dynamic functional connectivity maps for further analysis in the next step. We then took a completely data-driven approach to identify functional clusters within the hippocampus using a method called independent components analysis. And we then took these functional clusters and characterized how each of them preferentially interacts with specific cortical networks to show that different parts of the hippocampus are communicating with different parts of the brain. So the real take home from this is that we successfully combined this structural and functional data to get a much more fine-grained understanding of how these direct anatomical connections between the hippocampus and the rest of the brain facilitate functional connectivity. This really helps us build these more detailed models of human memory systems, and also has downstream implications for understanding hippocampal dysfunction in disorders that affect the hippocampus, like Alzheimer's disease. So thank you for your attention. Thank you to the wonderful team we put together to achieve this. So thank you.
Thank you so much, Marshall. One question there. So you talked about downstream consequences. Tell us about what kind of downstream consequences how would you like to use this newfound knowledge in these disease processes?
Well, it would be great to get data from patients, for example, in the early stages of Alzheimer's disease, mild cognitive impairment, and see if we can pinpoint specific parts of the hippocampus that may be affected very early in the disease process. And that would really help us develop these more reliable diagnostic methods.
I would have thought that the new insights of connections of other parts of the brain that are so tightly connected to the hippocampus would send you looking in the other parts related to that. Or am I completely off?
Well, yes, because the pathological processes that underpin, for example, early Alzheimer's start in other parts of the brain. They spread into the hippocampus. So yeah, looking at these areas that are directly connected with the hippocampus will give us these insights into what other areas we can target to look for those early diagnostic criteria. Yeah.
Thank you very much.
Thank you.
And with that, we bring up Sirisha Tarimala. Are you ready?
Walking slowly.
Set.
How do I press?
Green button there. Go.
Okay, hi everyone. I'm here to talk about the PRISM clinical trial. This is a trial that's aimed at making it possible for more patients with primary liver cancer to have radiation therapy as their curative treatment. So why is this important? Around 3,000 people in Australia are diagnosed with primary liver cancer every year. And there are several risk factors associated with these diagnoses. A lot of them may be very familiar to most of us. What happens is that these triggers cause chronic inflammation in the liver, which leads to scarring or fibrosis, followed by cirrhosis, where there's always a significant loss of function in the liver, followed by the cancer. 1 in 5 of these patients do not survive for more than 5 years after their diagnosis, despite treatments. So radiation therapy is one of the newer treatment options for primary liver cancer. And the goal here is to deliver high doses of radiation to the target tumor, while also not damaging too much of the liver tissue around it. So the way that clinicians decide how much radiation dose that can be delivered depends on the baseline function of the patient. And this is decided using blood tests. So the blood tests tell us if the liver function is good, moderate, or poor. And based on this, the clinicians decide if the patients can be treated, or maybe they are treated, but with suboptimal doses, or they are not treated at all. This is because the blood test cannot give any spatial information, and this is not very useful in the case of cirrhotic patients who have good, moderate, and poor functioning parts of the liver, and the overall liver function does not describe that adequately. So the PRISM clinical trial is aimed to personalize radiation therapy using liver function maps derived from MRI. And the way we get these functional maps is by using a MRI contrast agent that is injected into the blood. And is it playing? So this is a really advanced sequence that manages the motion of the liver really well, and I cannot tell if it's playing or not. So the blood comes in through the aorta, as so, and then it's taken up into the liver tissue. And regions of the liver that are high functioning take up more of the agent. They appear brighter in the image. But this is a very qualitative view of the way the liver is functioning. What we want to do is actually convert this using mathematical models into a quantitative map of liver function. And this will be a three-dimensional map. And you can look at different regions of the liver with high and low functioning. And in this example, for example, you see the blue is low functioning liver and the red is a high functioning liver. And so we know which regions to protect and which regions to target. And so in the clinical trial, we're recruiting 30 patients. This is underway at Westmead Hospital. Cheryl, thank you for mentioning that. And we will be scanning these patients 3 times, once before treatment, once during, and once 3 months after their treatment ends. And we will use this data to create a predictive model of function and decide how much radiation can be safely delivered to high functioning regions, allowing for personalized radiation therapy. What this means is that patients who do not have the good liver function as defined by blood tests can also be eligible for radiation treatments. So if you have any more questions, there's more information on our website of the BIRD team, and you can always email me.
So the post-processing is where the magic happens. Is that correct?
Yes, in a way, yes.
And how do you envision the step to clinical implementation? Is this amenable to be potentially integrated on the scanner, or is it something that requires something that is offline processing that is very resource intensive or something like what's the goal?
Yeah, so at the moment, it has to be offline, but it will be eventually, my vision is that it'll be similar to how you get K-trans maps on the scanner. So you would get a function map on the scanner, and it would be identical to be like that.
Don't we all have that ambition? Yeah. Thank you very much, Risha. Okay, next speaker. Welcome Sikong Tu to come up for the next presentation. Pull up the next one. So the green button is to start, red is to go back. Ready?
Yeah.
Set.
Okay.
Go.
Morning, everyone. So today I'll be talking about some of the imaging work our group has been doing in motor neuron disease, or MND. So MND is a complex disease that impacts both the central and peripheral motor systems. And one of the main reasons why it's so hard to develop effective disease markers to monitor disease progression is the inherent clinical heterogeneity. And while clinically there are useful objective markers for low motor neuron dysfunction, upper motor neuron dysfunction really remains a challenge. And this is really what we want to target with imaging. Yes, we want to target with imaging for the sake of patient monitoring, but also potentially for applications in clinical trials. So our group has done a lot of extensive imaging to try to comprehensively capture what can be seen in terms of MND pathology using MRI. So we know there are certain radiological features that can support diagnosis, in particular with the more regionally limited phenotypes of MND. We know that at its core, it's impacting the motor cortex, corticospinal tract, as well as the corpus callosum. But also there are significant fine-grained patterns of subcortical change, which in particular in the thalamus, which impacts disease progression rate. And these patterns differ between familial and genetic forms of MND, but also there is an overlap with frontotemporal dementia. and also longitudinally, we know that while the disease may start in the motor regions, it's not confined to it. So over the course of disease, it spreads quite far throughout the brain. So right now, we have a good understanding of what the pathology looks like. The next step is really distilling this information to focus on what is actually clinically translatable, so will impact the individual patient. And there are significant obstacles for each of these. So one modality that we are focusing on right now is MR spectroscopy. And when you consider the neuropathology of MND, like in the early stages, the primary pathology really is the motor cortex. And a lot of the neurophysiological studies in our group have shown that in the earlier stages of disease, and even in the pre-symptomatic stage, the motor cortex becomes hyperexcitable. So there's an imbalance in excitatory, but also inhibitory interneuronal circuits. What we've now shown with the MRS is that when we combine, so the metabolite basis underlying what was causing this hyperexcitability was relatively unknown. What we've shown with MRS is that there actually is a significant increase in glutamate that is underlying the cortical hyperexcitability that we're seeing in disease. The other issue that we had in imaging is it's very noisy. There's a lot of distribution and variability in the patients, but we found that by actually combining the neurophysiology as a stratification approach, a lot of that noise is being separated out. So what we were seeing before with just the raw imaging data was that there was a lot of bimodal distribution. But more interestingly, what we're surprised by was the longitudinal changes in MRS. So this was a very early slow progressing patient that we detected. What you can see is that the metabolite changes remain relatively stable while the patient remains stable, but actually precedes the clinical progression. And this is one of the primary aims of, so further validation is one of the primary aims of our group's most recent NHMRC result. And we think has very strong potential for being developed as a clinical monitoring marker for upper motor neuron dysfunction. Thank you.
Thank you, Zikon. So I experimented once with spectrum, and I learned humility trials of the condition, and in particular the post how the best things develop in the brain. How robust is it? How robust is it? You feel it's. You have to compensate for noise, but include noise, but include lots of subjects. Aside from the physiological noise, if you do repeatability in the same subject, how robust is the methodology?
So it really depends on the acquisition. Once you get the sequence set up, optimized, as long as the radiographer is consistent with the single voxel, that can be reliably quantified quite reliably. Post-processing had, well, I'm not sure how far back you're talking about, but I feel it has progressed significantly. The other thing I didn't mention is as part of the grant and also our collaboration with the UQ is developing multivoxel MRSI sequences. And this was one of the direct comments we got when we showed some of these results to our industry collaborators. Are you interested in potentially developing this as a marker for future clinical trials? And their answer is, how do you reliably scale this to like 200, 300 clinical imaging sites? So with the MRSI, it's a multivoxel approach that requires much less limited sort of precision at the single voxel level. So that's something, maybe I can talk about next year's summit.
Yes, thank you very much. And we have our next speaker, Kathy Willison. Kathy, welcome up. Green button forward, red button back.
Got it.
Ready?
Timer on.
Set. Go.
Well, thanks for having me here today for this very brief presentation. Instead of trying to race through a research project, I thought I would just try to convey a snapshot of our new total body PET system, which Steve introduced so wonderfully before, which is based at Royal North Shore Hospital. And in particular, I want to talk about the clinical impact that we're seeing from this system. Oh, do I need to point it? Yeah. So I really want to highlight today the flexibility of this amazing piece of technology, and not just the flexibility of it, but really how that translates into flexibility in the clinic and really changing our clinical practice and our day-to-day treatment of the patients. So first of all, fast imaging. So we used to acquire a standard FDG oncology study for about 20 minutes duration. We've been able to drop that down to 5 minutes with a view for dropping that further down to a 3-minute duration acquisition. And the image quality we get from these studies is still a vast improvement to what we had previously. So fast imaging is fantastic for us, and it's also, of course, really fantastic for our patients. Low dose imaging. So we've now decreased or reduced the FDG that we inject for our standard clinical studies by 40%. Huge dose reduction for our patients. Obviously, this has cost-saving implications for us, but also it's really beneficial in particular for certain cohorts of patients. So things like our pediatric patients, and in particular, patients who are coming back from multiple scans. We want to look to reduce that radiation dose wherever possible. One of the probably most exciting things about this scanner is what Steve was referring to a bit earlier, which is this idea of extended field of view parametric analysis. So because we have the heart in the field of view for the entire duration of our acquisition, which you don't have for a standard PET machine, it means that we can use those left ventricular contents to derive a time activity curve. And so we've got an input function to go ahead and develop that parametric data at the voxel level, as Steve was referring to. It's very exciting. There's a huge amount of potential for this in the research space, but also in the clinical space. And he spoke very briefly about, is it ready for clinical use? Well, we're actually exploring it already in our prostate cancer patients. So just in a handful of patients so far, looking at doing a 10-minute dynamic acquisition as opposed to a very long one. It's much more clinically manageable. And already we're seeing some really promising results from just 10-minute dynamic KI images compared to their standard clinical protocol. So that's a space to watch. X-ray dose reduction is another thing with this scanner. So because there's a tin filter on the X-ray beam, we're actually able to significantly reduce the X-ray dose associated with these studies. And whilst we're not routinely doing this in the clinic yet, it's something that we're really interested in exploring. And I think it'll be very valuable for research patients. And again, those patients who are coming back for multiple scans. And there are reports that you can reduce that by up to 90%. We get a great improvement in our image quality compared to previous scanner generations. And as I mentioned, also an improvement into the running costs. We have the option to do both studies on one day. So this really applies to, in particular, things like our neuroendocrine tumor patients who are having dual scans, so 2 different radiopharmaceuticals. But because we're using a PET machine, we're always imaging 511 keV photons, so we can't discern those signals from one another. So normally these patients would return on different days for those imaging. But because of this technology and the great sensitivity we have, I feel like you're sneaking up on me, we can actually look at trying to do these studies on a single day, which again, for our patients, this is just such an improvement. Late time point imaging, really exciting. The sensitivity allows us to image things days after injection. On the right, you can see an example with only 6 megabecquerels in the field of view, which is amazing. And last of all, I'll finish because this is just a really exciting piece of equipment, huge potential both in clinical applications, but also, of course, research settings. You're making me nervous.
Thank you so much, Kathy. So you've had a lot of hands-on experience with the new machine and the system. So there was there's hopes when you're trying to purchase and procure. How much of the hype truly delivered from your perspective? What was the most exciting part for you to see that actually was in real life and not just vaporware at the sales pitch?
I think Steve will agree with me. When we got that first full extended field of view study on our first patient, it was just the most beautiful image, really incredible image quality. The resolution was fantastic. And then when we extended that to a dynamic study, yeah, really, really incredible. We've got one of our clinicians, Sally, is here, and I think she'd agree that it's made a big difference, a big shift for their clinical reporting, getting used to the new SUVs and things like that. But there is so much more to see. Yeah, so it is exciting. Worth the effort, I hope, Steve. You did most of it.
Thank you, Kathy. And James Grover. Welcome, James. Ready? Yep. Green button.
Let's go.
That's forward. One's back. Set.
Awesome.
Go.
All right, hello, I'm James Grover. I'm a PhD student at the ImageX Institute. So we're about a 30-minute walk over the other side of Redfern. So if you want to get your step count up, just come visit us. So some background, I work in radiation therapy, and about 50% of cancer patients will be indicated for radiation therapy. And typically how this works, at least in the external beam context, a linear accelerator will deliver radiation to kill a cancer. And this will also damage healthy tissue. And this can induce treatment-induced side effects. And as we're all sitting here, hopefully we're all breathing and our hearts are all beating, and we could imagine this could cause targets to move in the patient. And as a result, the radiation can miss. So a novel technology, which has been discussed previously, is looking at real-time beam adaptation. So looking at adapting the beam to the moving target in real time. And really the research question that I was mainly involved in was, can we use AI to improve this beam tracking? So our work is really looking at MRI. So MRI guided radiation therapy is again a new field. And the how motion is detected is through real-time cine MRI. So currently, to keep the latency of adaptation low, the image quality is quite low as well. This is mainly in part due to the low spatial resolution. So can we apply super resolution, which is an AI technique, to make these images better in real time? So we have access to the Australian MRI Linac, and that's it on the right. And this is in Liverpool Hospital. So that's a very long walk if you want to walk there. And we also developed a custom deep learning framework that integrates with Gadgetron and adaptation. So just briefly, the MRI Linac will stream data to Gadgetron that'll reconstruct an image. Our deep learning framework will then make a super resolution image, which will be fed to the adaptation software that will adapt the beam in real time. So some results, here are some image quality results. So for about a 5 millisecond penalty to the latency, we can improve the image spatial resolution as shown. So the key takeaways is that you need to be very careful about how you generate your training data. So for example, if you're using synthetic data, that may really impact the results when you're testing on real data. Also, the normalization you use, the distribution of the data should be roughly the same as when you're inferring. And also anatomical sites. If we're training on different anatomical sites, we should be aware that the performance may not be the same for other anatomical sites. And really, open source software really enables this research, such as the Gadgetron. So I support all endeavors to make your code open source. And we have a paper on the way, so stay tuned. I'd like to acknowledge all the great people behind this work, and thank you all for listening.
There was a very quick jump there, paper on the way. Is it, was it accepted already?
It's accepted. We've got a couple of changes before it'll be published.
Okay, so it's not accepted yet, or it is accepted yet?
It's accepted.
Provisionally?
Yeah.
Okay, well, congratulations, that's great.
Thank you.
And so when it comes to super resolution, it can be applied in the spatial domain, but it can also be applied in the temporal domain. Did you, would there be any advantage with reducing the temporal resolution and using super resolution in the temporal domain to get the balance of spatial and temporal resolution?
It's an interesting question. So currently you can image it around 4 hertz for real time, like as I showed there, 4 or 8 hertz. I'm not sure if there'd be much an advantage if we bump that up to say 12 or 16 hertz.
Or go down in imaging.
Or go down in imaging.
With then better spatial resolution at per acquired image.
Yes, I think.
Good answer.
Yeah,
well,
that's the answer.
I don't know, but I don't know the trade-offs of working in those with those parameters, but it might be something worth looking at.
Yeah, awesome. Thank you.
It's the images look spanking good.
Thank you.
Yeah. All right. Kiri Barlow.
I'm Kiri Ballard. With funding from ARC, our group are using dynamic MRI to capture and model articulatory coordination during speech. central challenge to understanding how motor control for speech develops is comprehensive visualization of the vocal tract during the act of speaking, simultaneous visualization of the tongue, lips, jaw, palate, and larynx. The current tools provide limited information, primarily two-dimensional, and focused on tongue movement or tongue-palate contact patterns. With dynamic MRI, we can capture the entire length of the vocal tract during speaking. This is one of our mid-sagittal scans, giving an example of the images and audio captured during a single word task focused on vowel articulation, varying the vowel in a constant environment.
Bit, bed, mat, bat.
We can also collect 3D volumetric scans of sustained speech sounds. We have two main streams of work that we're doing in the research imaging facility at Westmead Hospital with Cheryl Foster and her team. First, we're developing tools and methods. By collecting both dynamic mid-sagittal MRI and volumetric scans of static postures, we can build 3D vocal tract models, as you can see at the top, and utilize the 2D scans to guide large deformation diffeomorphic mapping to generate in future 3D dynamic models of articulation. We're quantifying vocal tract shape variation and its acoustic impact using approaches such as geometric morphometry. And we're exploring multimodal neural network models to effectively fuse video and audio streams to improve automated speech classification. Applications of this work include more accurate acoustic to articulatory inversion for automatic speech recognition and analysis, computer-aided speech and language learning, and personalized speech synthesis for those without speech. Second, we're developing knowledge. We're collecting data from adolescents and adults to inform the mapping between goals of speech production in acoustic and articulatory domains, the sources and limits of individual speaker variation, and how that differs with gender, rapid growth, such as in puberty, bilingualism, in our case, we're studying English and Mandarin, and in future, the intention is to develop broader collaborations to investigate how speech changes with structural and neurological disorders or rehabilitation. And the system can also be used for studies of other head and neck functions, such as swallowing and singing.
Can you confirm with a nod that that was the end of the video? Okay, we got that. It was the whole thing. So no opportunity for Q&A. I know there's been a lot of work in the speech space, optimizing the acquisition side of things to coordinate that with the audio, which is a major challenge. You would have heard the sound and that you could hear the gradients going in the background. There's been a Herculean effort to get those kind of things going in the field. And I know that Kiri's worked real hard with her team to try to make that happen. So the next speaker is Jinglei Liv. And please welcome to give your presentation.
That's forward. That's back. Okay. Are you ready?
Yeah. Okay. Great. Sorry, it's very challenging. Yeah. Go. Yeah. So, sorry. It's a very good pleasure for me to introduce our new method to map the functional role of white matter. So this is a teamwork with Fernando and with Professor Mike Shan. If you're familiar with functional brain mapping, functional MRI plays a major role. So basically, we design the task, then we mirror the both activity. We compare the two. With generated model, we can generate this beautiful task execution. We know that white matter also play an important role in the brain function, but there lacks method to explore this. The viewer MRI help us to map the white matter tracks. So we ask whether we can combine the viewer MRI and the functional MRI to explore the functional role of white matter. Here we define the track dynamic functional connectivity. So it's a new time series which is defined by the two fMRI time series of the green matter
So the two work cells are connected by one single track. So this time series reflect the functional synchronization between the two gray matter ends of one single white matter track. So on the right, you have seen the animation. So we can see a lot of dynamics in the functional synchronization. And so this is about the resting state, but we can also calculate the dynamic functional connectivity for the task. And we can compare our time series with the task design. With general linear model, we can map the task actuation to the white matter tracks. On the right, you can see some result. However, one big challenge is the individual variability. Assume that we track fibers for 3 different subjects. Even we set the same parameter, we use the same number, they not necessarily have the correspondence. To address this, we have developed the multimodal tissue unbiased burn template. In this template, we have the structural components, different components. Importantly, we have this tractogram template. So it is firstly tissue unbiased. It's well aligned with the cortex and the subcortical nuclei. And this helps us to find the right fMRI signal for each track. Then, so we align all the fMRI data from each individual, from each task to the task space, to the template space. Then we use this tractogram template to generate the track DFC. And finally, we can do the group-wise analysis. We can detect a robust activation for the tracks. So we tested this idea with the Hemming connectome data. And here I use the motor task as an example. So for each subtask, we can map the white matter activation. And this agrees quite well with the homunculus. Most importantly, we compare our result with the traditional activation. We see that this activate the tracks not only connected to the traditional activation, but it extends to other regions, and there are also independent fibers that connect into other regions. This suggests the network pattern of task activation. So we have more results. We are working towards a functional atlas of white matter. Thanks for your attention.
It's tricky to stay on track with the time. So for when it comes to applying this, I mean, I asked a similar question before of a previous speaker, but is this something that you could see scaling to hundreds of patients or thousands of patients, or this is a Herculean effort to get one patient analyzed with these kind of methodologies?
That's a very nice question. So firstly, we aim to generate the atlas, which will be important knowledge for clinical inference. And we also aim to develop individualized mapping. So we can collect the individualized different MI and the functional MI. And well, likely what we do for the epilepsy patients, we map the language network with fMRI. So we can also map the relevant activation to the white matter tracks, so that when the clinicians do the surgery, they can avoid such regions. Yeah.
Thank you very much.
Yeah. Thank you.
And next up, we have Veronica Wong. Welcome, Veronica. There's forward, there's back. Are you ready?
Yes.
Set, go.
Thank you. Hi, everyone. So I'm a clinician researcher with a research background in endocrinology and nuclear medicine. And together with my colleagues at Nepean Hospital, we've been working on using dosimetry to revisit one of the oldest known therapies for cancer, iodine-131 or radioiodine. So radioiodine has been used as an adjuvant therapy for treating thyroid cancer since 1941. We know that radioactive iodine specifically targets the thyroid with very little effect on other tissues. However, decisions about how much to give has traditionally been based on standard dosing, so really guesstimates about what the patient actually requires. So dosimetry involves determining the ideal dose of a therapy to maximise its efficacy and to minimise the side effects on other tissues. In nuclear medicine, because the therapy is systemic, consideration needs to be given to the burden of disease, the treatment target, the pharmacokinetics, including the excretion, which typically is through the urine, and radiation exposures of healthy tissue, most pertinent being the bone marrow and also the salivary glands. So to demonstrate these concepts, I will present 2 cases of patients with a background of end-stage renal failure requiring dialysis who were referred for radioiodine therapy. In renal failure, the patients don't excrete effectively, and so therefore there'll be a slower removal of the radioisotope from the circulation. The increased effective half-life will therefore increase the radiation dose to the bone marrow, which needs to be balanced with the treatment intent of radioiodine to ablate the remnant thyroid tissue. So in our first case, this gentleman had a bilateral nephrectomy for polycystic kidneys. And based on the imaging, you can see that there's not much uptake in the thyroid gland in the thyroid bed. In fact, most of the activity accumulates within the salivary glands and the stomach within the first 20 hours. And a lot of that also distributes through the blood as well. Following that, there's excellent clearance from the body following 1 session of dialysis, which mimics what we would expect in someone with normal renal function at 27 hours, and furthermore, again at 75 hours. In case 2, this patient actually had a higher body mass and had a colostomy. And based on the imaging, you can see that he actually distributes faster within the blood. There's much more activity in the thyroid bed as well as the salivary glands and in the stomach. And he had an earlier distribution in the circulation, which was a little bit different to patient 1. And using these images, we can predict the residence time of the isotope in different organs and therefore be able to predict how to determine the dose to maximise its efficacy. We can also overlay the whole body retention of activity compared to patients with normal renal function. So in our 2 patients, which are in the blue lines, they actually retained a lot more of the isotope with a slower body clearance within the first 24 hours. The first dialysis session really effectively reduces the amount of radioactivity, much like their counterparts with normal renal function. And we hypothesised that in the second patient, he had a higher residence time of the isotope because he had more residual tissue left over from the surgery. We can also show that the clearance rate from the blood clearly matches that of the radiation activity through the dialysis excretion. And both patients did not exceed the maximum recommended marrow exposure of 2 gray, which potentially means that we could give further higher dose treatments in the future. So in conclusion, pre-treatment imaging may help to inform this. It may be possible to give a small diagnostic dose of I-131 or I-123, and we'd be able to determine the potential residence times in different tissue sites. We'd also be able to answer historical concerns about the potential for stunning following radioiodine. And so overall, we'd like to try and rethink how imaging can influence thyroid cancer management and deliver a more personalised approach. Thank you.
Thank you very much. So you've done these first 2 patients. You've established an hypothesis about this. What are your thoughts on study design moving forward to bring it home and prove this on a more generalized scale?
So I think there's always going to be a heterogeneous population pool, and ideally we'd like more patients with renal failure, but it depends on our referrals. We'd like to be able to determine or identify patients that actually have a lot more residual tissue before they actually receive their treatment. So unfortunately, a lot of the imaging happens after they've received the treatment. So if we can shift the time frame of the imaging earlier to perhaps develop better ways of imaging them without the potential for stunning, we'd be able to translate that into, being able to deliver a more personalised dose.
Is there a patient throughput at your department that would enable you to do 20, 30 patients or something like that to get a little bit of numbers?
For sure, yeah, for sure. So we'd hopefully be able to collaborate with other centres as well, but currently we'd have all comers coming through and we'd have about 30 or 40 patients through in a year. So it'd be nice to collaborate with other centres as well.
I'd love to see those results downstream.
Thank you.
Thank you. And our next speaker is Payman Obeid. Welcome, Payman. Share your screen now.
No, I can, this is just only.
Oh, okay. Are you ready?
So which one? is
Let's
it?
forward.
Yeah.
Are you ready?
Okay, cool. Yeah.
Set?
Yeah. Thanks. Hi, good afternoon, everybody. I'm going to talk about the ground glass opacity and how we can detect this silicosis. But just before that, if you also was dazzled by the new AI, which came out 2 weeks ago, the point here is that apparently one of the challenges for this device, for this technology, or initial challenges, was to handle glass opacities. And it's interesting because based on these 2 studies that has been done with in our team, the human also sharing this difficulty, and we have problem segregating the ground glass opacity. We can do better with the nodules. To be honest, it's understandable why it's difficult. It's very complex, and then a combination on all of these diseases will, with the patient history, will make the diagnosis. And it also become more difficult than when you think about that, the latency between the time that someone was exposed to silica and the time that they gonna show the symptoms. It would be about 10 to 30 years, and having a higher risk of cancer. So to sort of solve this problem, over the last 7 months, which I embark on this journey, I put together a team to start building an infrastructure or a pipeline that allows bringing AI into the clinic as a plug-in, if you like. So I believe that when we have this infrastructure, any sort of device that you develop, then it can be just simply added to the infrastructure that we have. So it's a combination of the clinicians, industrial partners, and researchers, which are helping, and at the moment doing a discovery phase by patient 0 to use a highly secure platform on a Snowflake and make it much easier for us to bring our tools that we develop in. For example, this is an example of the tools that we have developed. So we said, let's learn from the COVID, collecting the images that's already there, plus the algorithm has been developed, and then we fine-tune it. And firstly, we took away all the difficult cases or the simple cases. So look at the more difficult ones. So improve the system and then apply it to silicosis cases. So at the top, we learned from COVID data, and at the bottom, we applied to the COVID patients' information. It's still a long way to go, but we're getting there.
So silicosis and or interstitial lung disease in the broader spectrum of things is a huge diagnostic challenge that is frustratingly difficult for the new radiologist getting introduced to it, because there's so many acronyms and there's such nuances in the imaging phenotype. How repeatable would you say the imaging phenotyping is using these AI tools, and is it as confused in its image analysis as the human is looking at it for the first time?
Yeah, I think you're pointing to a very good point. And yes, it is somehow confused at the beginning. And the way that we are helping it is by providing additional information. So we use multiple or combination of the algorithms. Some of them look at the location and some other look at the features. And then we sort of try to use the best of each. And also a point that we were discussing with Warren recently was from that confusion that we can see the algorithm does, and going back to the point that the confusion means that there were some sort of similarities in the trend that machine learned with this mistake that we say. And our job is to see if we can understand whether those mistakes is actually related to the early stage of the disease. And if we can tease those points out, then hopefully we will be shortening the time that we can detect this.
It's a formidable challenge. Good luck with that.
Thank you.
And our next speaker is Hallie Kwong. Welcome, Hallie. Forward, back.
Yeah, sure.
Ready?
Thank you.
Set,
Yeah,
go.
sure. Hello, everyone. I would like to start with three main challenges in dementia. Firstly, diagnosis is challenging. Second, prognosis is uncertain. And lastly, treatment is unavailable. So key to these big challenges is to identify a biomarker that can reliably characterize or reflect the underlying neurodegenerative mechanism of dementia. So imagine the brain as a complex network of interconnected highways with white matter serving as the infrastructure, facilitating the communication between different regions. So if there is any changes to this vital infrastructure, of course, like disruption to the traffic and to the flow will occur. The same thing happened to dementia. However, the issue is our brain is much more complicated than even the most complex highway system in the world. White matter network in our brain go everywhere into different dimensions. Therefore, characterizing white matter changes is very, very challenging. And thanks to the development of neuroimaging techniques that already be presented by our previous speakers, we're now able to precisely map white matter changes associated with dementia. And this one of the techniques is called fixed-base analysis with further development from our SYNC network. And in my talk, I will go precisely how this is going to show the potential to answer important clinical questions in dementia. Firstly, for diagnosis, white matter changes show a strong association with clinical symptoms. For example, we have here clinical symptoms of dementia are quite challenging to differentiate. For example, apathy and empathy loss can be very similar on the behavioral level. However, by using the white matter technique, we are able to show distinct white matter correlates to different clinical dimensions. For prognosis, white matter imaging serves as a reliable proxy for checking disease progression. For example, here we have brain scans of patients with behavioral variant frontotemporal dementia. At baseline, white matter atrophy can be seen in the frontal and temporal lobes in the brain. However, over the time, we can see that the white matter atrophy spread to a more distributed network, significantly predict the changes and widespread functional decline in patients. And this even precedes clinical symptoms many years. Lastly, in terms of treatment, white matter integrity is associated with pathology. So we know that in dementia, pathology usually occurs first, leading to atrophy and finally clinical symptom. Targeting clinical symptom is already too late in dementia. However, targeting pathology is too hard. Therefore, now that we are able to identify the white matter changes associated with pathology, we will be able to monitor and track disease target treatment more effectively and early on. So I hope that in 3 minutes, I somehow convince you to believe that white matter is not, white matter techniques is not only cool, but also have some clinical importance. Thank you so much for your attention.
So would you say that this is on the level of technical methodological development, or are you starting to get a feel for the diagnostic performance in patient groups?
I think I would say in between. So of course, there has been some development in the technical viewpoint over the past couple of years. But then like for like clinical application is also a very important aspect. And in order to be able to like make accurate diagnosis individually, I think we need to like do more work to be done in the field. And of course, like individual mapping is very important.
Thank you very much.
Thank you.
Best of luck. And now we have Mariano Cabezas. Bring back forward, bring back. Perfect. Ready?
Right. Is it to do like that?
Yeah, let's see. Do one more.
Yeah,
One
something, I guess.
Do one more.
Oh, okay, sorry. That's me.
Okay. Ready, set,
Yeah.
go.
Okay, hello everyone, and in the interest of going fast, I tried to prepare this presentation as a sort of short pitch about a side project I've been working on in the last couple of years. I'm going to answer what is it about, why is it important, how have we done so far, basically methods and some brief preliminary results, and who. And I apologize because this is the best who image I could find with Google search. So it started with the ambitious idea of developing a longitudinal normative fetal brain model, so ambitious that a big consortium released a paper during the last year at the end of December, and these are some examples of this written plate. However, to start with this project, we focused on week 20 and 2D ultrasound to generate this atlas. Why 2D ultrasound? So international guidelines advise to acquire 2D ultrasound during 2 different time points of pregnancy. One of them is around week 20, and this is to look for abnormalities. And why not 3D? So 3D ultrasound is not extensively used worldwide, and it has additional issues on top of the common issues that you would find with 2D ultrasound. And why not MRI? And I just realized that the image is cutting the text. So why not MRI? Because it's not more sensitive during the first 20 weeks. And even though it's also used once you detect abnormalities in 2D ultrasound for further checks as a complementary image. Moving on to the how, the data we acquired is from around 60 pregnant women, some of them multiple scans, just to do some scan-rescan check for consistency. And these images were manually annotated by an expert, highlighting landmarks, so points that appear on all the images, for some important structures during brain development on the fetus. During going to the methods, so we used a multi-step process. This is step 1, where we segmented the brain circumference, and we used a public data set of around 1,000 images, where the skull was segmented, fitting an ellipse. As you can see, which is not a perfect segmentation of the skull. And we use a deep learning model, a UNet, which is the most commonly used method to segment images, to segment these images into a rough segmentation of the skull. This is an example where you can see that the segmentation is not perfect. This is not important because once we move into the second step, following this idea of an ellipse to represent the head circumference, we use an iterative process where we take all the points from the segmentation and we try to fit an ellipse, which is represented by these properties here, basically central point of the ellipse, the angle of rotation with respect to the horizontal axis, and the length of the major and minor axes. And then using this information, which is basically a mathematical equation, and the image dimension, we can define a transformation, a rigid transformation, that we can use for all these images to put them on a common space. What that means is that we don't need a reference image, and for each different image, we acquire this transformation. And here are some examples where we move all these images to this common space and the points. These points can be used for 2 things. One is making sure that all the points align. And the second one is using some very basic computer vision and computational geometry methods. We can define some masks for these different regions, and then we can create probabilistic maps or just one map for each image. Finally, and I'll see you coming down there, I would like to thank the people that have made this international collaboration project. It's all Spanish people, but it's from one hospital that has provided the images, Clara and Anna from Hospital Josep Truet in Spain, and from Yamagata University, Iago Diaz in Japan, that helped me with the method design and implementation. And that's it. Thank you.
So image quality on the ultrasound side of things, how challenging has the image acquisition or the quality of the images coming through been in relation to the development of the post-processing methodology?
So we try to choose a methodology that can go beyond this. So the segmentation, as you can see, it's not perfect. So we have seen that the skull is not always well segmented. But the good news is that with this optimization process that we use next, we don't really need that good segmentation. So what I'm trying to say is that we have tried to look at methods that are independent of this quality, because we know it's an issue.
Well, yeah. Thank you very much. And our final speaker in the research showcase is David Waddington. Welcome, David.
Green goes. 3, 2.
Well, you're not there yet.
1, go.
Are you ready?
I've already started.
Okay.
Anyway, all right. Thank you. All right. So the low field portable MRI scanner coming to UCID in 2024. We'll get there in less than 3 minutes. Okay. First, maybe I'll just touch on, okay, why low field MRI? Well, and also I guess it's already kind of here, but why do we want it? Well, first of all, we've heard that MRI scanners are pretty expensive from Fernando this morning, and it kind of makes it hard to get them in where you want them when you want them. So low field scanners are cheap by going to permanent magnets, electromagnets. They can be much lighter as well. It means you can put them wherever you want. Well, maybe not wherever you want, but in lots of different places. Save millions of dollars on building costs, amongst other things, around a cost of living crisis. And on top of that, from a practical perspective, there's a lot of fewer contraindications. So things around claustrophobia, but then also things around different kind of implants and things that might not be compatible with high field strengths. But from a clinical perspective, I think it's really this portable aspect, the idea that you might have an unstable patient in an ICU, for example, that you can bring the scanner to them without needing to move them to the scanner. So there's a couple of systems out there. There's a Promaxo MRI aimed at prostate interventional surgery. There's also a hyperfine swoop scanner at 64 millitesla. So the hyperfine swoop. So as of last year, a bunch of people here in the room helped me out with a CapEx application. So an $850,000 application that's been approved for a purchase of one of these scanners. So it's funded for a variety of research and teaching use. It's going to live in the Susan Weichel Health Building. The vision is in a couple of years' time, there's going to be a bridge that connects the Susan Weichel Health Building across into RPA there for clinical studies. So it's going to be able to move between those two locations, really be part of that whole health precinct. And I guess really sort of this system is really primarily aimed at neurocritical care, so brain imaging, but then also are opportunities to use it in pediatrics. Yeah, so maybe, of course, it's not all bright and shiny. With low field MRI, there's a big signal to noise issue. So roughly magnetic field strength to the power of 3/2. So back of the envelope, you might say that one of these 64 millitesla scanners, it could take maybe 10,000 times as long to take an image. That's a problem. There's lots of things you can do. There's lots of fancy technology. I just want to give you a window into some of my research program where we're looking at using different AI reconstruction methodologies to improve these images. So this is something known as an unrolling reconstruction network. It really integrates a lot of the MR physics of image reconstruction with convolutional layers to try and get better images faster. So in this case, we're looking at an example where we've sampled of order 25% of the imaging data. And imagine I get a laser. I don't get a laser. Oh, well. So you can see that we've got this unrolling network, this thing that we've been working on. Top right, that image is 25% of the imaging time. It's what you might see on the top left. And so these are the kind of things we're working on. But to finish up, coming next year or this year, being purchased this year. Lots of teaching and research potential. And get in touch if you want to be involved and want more information. Thank you. I'll let Martin round it out.
So before you go, David, thanks for putting in the fantastic work to get it here. You said it'll be in the Susan Wickell Health Building, but the patients that are interested to be imaged would be in the hospital. Can it roll across the street?
Well,
in the absence of an air bridge?
Well, the approved building plans there's lots of pugs and other things.
No building. Can it, if it arrives next week?
If it arrives next week, can it roll across the road?
Yes.
Yes, you could do it. Would you want to do it every day? No, like it's just.
But
like if you were like, I have a big imaging study, it's going to run for the next month, and it's going to be there. Like, let's get a bunch of people. We're going to do this. You could do it. Yeah.
Get a big umbrella.
You could do it, but AirBridge is coming, and then you could do it sort of in the space of like, oh, I've got this patient. Give us half an hour. We'll get a scanner there. Yeah.
Important information. Thanks.
Yeah, cool.
So we have two finalists and a winner. And because we have to have drama here, right? A little bit of drum roll and think so. So there's the drum roll, and I'll bring up the two finalists at the same time for a simultaneous photo, and they are James Grover and Chandrama Sengupta. You come over here. This, and a shake of the head. Well, congratulations. And oops, sorry, the phone, yeah. And then there's the finalist. Oh, gotta photo up. And now, the winner of the Sydney Clinical Imaging Summit 2024 Best Presentation Award goes to Marshall Dalton. Congratulations to the winners, and thank you all for coming today. We now have the lunch aspect, which I hope you've all been patiently waiting for. We've been decently adhering to the time, and the lunch is all served here with the mingle here. Do we have any final? And then, and of course, we have the team behind the team. This all today would never have been possible without the support of the fantastic AV crew and but especially the fantastic organizational skills of Nicola Bignanos, who's been taking care of us all and making this happen. Thank you, Nicola.